Hello and welcome to Sleepy Science Tonight. We're drifting into the quiet edge of quantum reality, where light behaves like a wave until it lands. Matter loses its solid certainty, empty space is not truly empty, and the smallest pieces of nature refuse to act like tiny versions of the world we know. We'll move through 30 calm and curious ideas. Why particles do not choose paths the way we imagine. Why probability may be deeper than certainty. How measurement turns potential into one result. Why quantum states can be as fragile as soap bubbles. And how the classical world around us may be a smooth illusion rising from something stranger underneath. By the end, I hope reality feels a little softer, less obvious, and more mysterious in the most beautiful way. Before we begin, tell me in the comments which quantum idea feels the strangest to you. And if these slow journeys help you relax, think, or see the universe differently, tap like, subscribe, and keep exploring with Sleepy Science. Light behaves like a wave until it hits the screen. Imagine a single spark of light leaving its source in complete silence, so small that you cannot hold it, so ordinary that your eyes have trusted it every day of your life, and yet so strange that when scientists follow it carefully, it seems to carry two personalities at once. One that spreads, blends, overlaps, and ripples like a wave across open space, and another that arrives suddenly, sharply, and indivisibly, like a tiny impact on a screen. This is one of the first doors into quantum physics, and it opens with something deceptively simple. Light behaves like a wave until it is caught as a particle. You may have seen waves before in water, in sound, in the slow rolling motion of a curtain when wind passes through a room. A wave does not have to choose one narrow lane. It spreads, it bends around corners, it overlaps with other waves. If two waves meet, they can build each other up, making a stronger wave, or cancel each other down, leaving a quiet patch where motion almost disappears. Light does this too. Long before quantum physics, scientists already knew light could act like a wave because it creates interference, the same kind of pattern you get when ripples on a pond cross paths. One of the clearest ways to see this is the famous double-slit experiment. You shine light toward a barrier with two narrow openings, and behind that barrier you place a screen. If light were only a stream of tiny pellets, you might expect two bright bands behind the two openings, as if little grains had passed through one slit or the other. But that is not what appears. Instead, you see a series of bright and dark stripes. The bright stripes appear where the wave-like parts of light reinforce one another. The dark stripes appear where they cancel. This pattern is not random decoration. It is the fingerprint of wave behavior. It says that light, while traveling, is not behaving like a simple object moving through a simple path. It is spreading through possibility, passing through the arrangement, in a way that allows different routes to overlap and interfere. But now comes the part that makes the mind slow down. If you reduce the light until photons seem to be sent one at a time, the screen still records them one by one as separate dots. Each photon lands in one place, not as a smeared out splash across the whole screen. It arrives like a particle, a tiny localized event, one flash, one mark, one impact. And if you wait long enough, dot after dot after dot builds the same wave interference pattern. This is the quiet miracle. Each photon is detected as a single point, yet the full collection of points reveals wave behavior. It is as if light travels with the grammar of a wave but speaks to the screen with the punctuation of a particle. That does not mean light is secretly just a wave or secretly just a particle, and we simply have not found the right label. The deeper lesson is stranger and more honest. Our everyday labels are too small. A photon is not a miniature tennis ball, and it is not a little ocean wave either. It is a quantum object, and a quantum object does not fit neatly into the pictures your senses evolved to understand. The wave part is not necessarily a physical ripple in space like water rising and falling. In modern quantum thinking, it is better to think of it as a wave of probability, a pattern that tells us where the photon is more likely or less likely to be found when it finally interacts with something. Before the screen catches it, light is described by a spread of possibilities. When the screen absorbs it, those possibilities end as one recorded event. This is why the screen matters. The screen is not magical. It is not conscious. It does not need to look in the human sense. It is simply a physical system that interacts strongly enough with the photon to leave a mark. The photon gives its energy to one small region of the screen, and that is the result we see. Before that interaction, the photon's behavior can create interference. After that interaction, there is only a spot. The wave-like journey becomes a particle-like arrival. This is not a lie told for mystery. It is one of the most tested facts in physics, seen not only with light, but with electrons, and even larger quantum systems under careful conditions. But light is the gentlest way to meet it, because light is already part of your life. It is the glow on your wall in the morning, the reflection in someone's eyes, the soft edge around a street lamp in fog. You think you know it because you live inside it. But quantum physics asks you to look again. It asks you to notice that reality may not be built from little solid things moving along little fixed roads. At its deepest levels, nature seems to carry patterns of possibility that only become definite when an interaction forces a result. This does not mean anything can happen. Quantum physics is not chaos pretending to be wisdom. The probabilities are precise, the pattern is reliable. The dots appear one by one, but the stripes emerge with astonishing order. That is what makes it so beautiful. The universe is not simply uncertain in a messy way, it is uncertain according to rules. It is like listening to rain fall on a roof. Each drop lands in its own place, but over time the sound becomes rhythm. Each photon leaves one mark, but over time the marks reveal a hidden structure. And this changes the way you think about seeing itself. You might believe sight is simple. Light leaves an object, enters your eye, and gives you the world. But even the light reaching you has this deeper story beneath it. It has traveled not as a tiny bead following a perfectly defined path, but as something that can spread, overlap, and carry information through wave-like behavior until it is absorbed by the cells in your retina. Your eye is also a kind of screen. It catches light in tiny events, and your brain turns those events into a continuous world. You do not see the wave of possibility directly. You see the result after nature has already answered one question. Where did this photon land? In that sense, every act of vision is a quiet negotiation between possibility and arrival. The room around you feels smooth and stable, but it is built from countless small interactions that have already become definite before they reach your awareness. And maybe that is why this experiment feels so haunting. It does not just teach you about light, it teaches you humility. It reminds you that the world does not owe your intuition an explanation in familiar shapes. For centuries, humans argued whether light was a wave or a particle, as if nature had to pick one of our categories. Quantum physics answered by refusing the category. Light can show wave behavior in how it travels, and interference behavior in how possibilities combine. Yet it can show particle behavior in how it is detected and exchanged as energy. The truth is not halfway between wave and particle. The truth is deeper than both. The wave and the particle are not the thing itself. They are the faces it shows when we ask different kinds of questions. Ask how light spreads, and it answers like a wave. Ask where it lands, and it answers like a particle. That should make you wonder how many other things in life feel simple only because you have been asking simple questions. How many certainties are just the shadow of a deeper process you cannot directly see? How many times have you mistaken the final dot on the screen for the whole journey that created it? A photon teaches quietly, but it teaches well. What arrives is not always the same as what traveled. What becomes visible is not always the full story. Behind every definite mark, there may be a field of unseen possibilities that shaped it. And as the last image settles in your mind, imagine the screen again, dark at first, then slowly gathering points of light. 1 dot means almost nothing. 10 dots still look scattered. But wait long enough, and a pattern appears, as if the universe was whispering through repetition. I may arrive in pieces, but I move with hidden order. That is the strange calm at the heart of quantum physics. Light does not stop being mysterious because we can measure it. It becomes more meaningful because we can measure it and still be surprised. It travels like a wave, lands like a particle, and leaves you standing between the two, not confused because science has failed, but awakened because science has shown you that reality is larger than the instincts you brought to it. Reality seems smooth, but quantum physics says it isn't. Imagine running your hand across a polished stone and feeling nothing but smoothness, as if the surface were one continuous thing, one calm sheet of reality with no hidden breaks, no invisible steps, no tiny separations beneath your fingertips. To your senses, the world seems seamless. A table feels solid from one edge to the other. A beam of sunlight looks like an unbroken stream. Water pours as though it were a single flowing substance. Sound rises and fades as if volume can change in perfectly smooth slopes. Even time feels like it moves in a continuous river, one moment melting naturally into the next. This is the world your body was built to trust. A world of curves, surfaces, flows, and steady transitions. But quantum physics begins with a quiet correction. It says that the smoothness you experience is not the deepest layer of reality. It is a large-scale appearance, a softened picture created because your senses are too coarse to notice the tiny structure underneath. Nature, when examined closely enough, does not always change in an infinitely smooth way. Energy can come in packets. Atoms can hold only certain allowed states. Electrons do not simply drift through every possible level around an atom like a bead sliding along a wire. They are found in specific arrangements, like notes on an instrument that cannot play every possible sound between two keys. This does not mean reality is fake, and it does not mean everything is made of little cubes like a video game. That would be too simple and not fully honest. What quantum physics really shows is more subtle. Many of the things that look continuous to us are built from rules that are not continuous in the everyday sense. The universe can appear smooth at the scale of hands, eyes, oceans, and planets, while behaving in sharply structured ways at the scale of atoms and smaller systems. Think of a photograph on a screen. From far away, the image looks soft, full, and natural. A face has curves, shadows, warmth, but come close enough and the image is made of separate points of light. The face was never false, it was just not the deepest description. In a similar way, the world you touch is not lying to you when it feels smooth. It is giving you the version your body can use. Beneath that version, matter is made of atoms. Atoms are shaped by quantum rules, and those rules allow certain things while forbidding others with astonishing strictness. One of the clearest examples is the color of light that atoms absorb and release. If atoms were like tiny solar systems where electrons could orbit at any distance with any energy, they would absorb and emit light in a smooth spread, but they do not. Each kind of atom has its own set of allowed energy changes, like a fingerprint written in color. Hydrogen, sodium, neon, mercury. Each produces particular lines in a spectrum, not every color at once. That is not decoration. That is evidence that energy inside atoms is structured in steps. A sodium street lamp glows yellow because sodium atoms prefer certain energy transitions. Neon signs shine with their own characteristic colors because neon atoms have their own allowed patterns. When scientists spread starlight into its colors, they can read dark and bright lines that reveal what stars are made of, even from enormous distances. This is one of the most beautiful consequences of quantum discreteness. The hidden step-like behavior of atoms becomes a language, and that language lets us identify elements across space. The universe is not smooth noise. It has a kind of internal music, with certain notes allowed and others absent. And this is where the word quantum earns its meaning. It does not simply mean small or strange. It refers to the idea that some physical quantities come in definite amounts, not in endlessly divisible pieces. A dim light can be made dimmer, but the exchange of light with matter still happens through individual units of energy. An atom can gain energy, but not just any amount in just any way. A hot object can glow, but understanding that glow required scientists to accept that energy is exchanged in packets. This was not invented to make science mystical. It was forced on us by experiments that classical physics could not explain. The old picture imagined nature as perfectly continuous, like a smooth ramp. Quantum physics showed that, in many places, nature behaves more like a staircase hidden under a carpet. From far away, the carpet looks like a slope. Up close, the steps matter. Yet we must be careful here, because not everything in quantum physics is simply chunky in the same way. An electron in an atom is not a tiny planet sitting on a tiny shelf. The allowed states are more like stable patterns, the way a guitar string can vibrate in certain natural shapes. You can pluck the string softly or strongly, but the string prefers certain modes of vibration. Quantum states are not little drawers where particles hide. They are structured possibilities that nature permits. This is why the smooth world can emerge from an unsmooth foundation. Large objects contain unimaginably many atoms and interactions. Their quantum steps are so tiny compared with everyday scales, and so densely layered together that they blur into continuity. A staircase with steps too small to feel becomes a ramp to your hand. A movie made of still frames becomes motion to your eye. A beach made of grains becomes a shoreline from above. Your senses are not wrong. They are averaging. They are compressing a world too detailed to experience directly into a usable picture. This is one reason classical physics works so well for falling stones, rolling cars, swinging doors, and orbiting planets. At our scale, the quantum structure usually blends into smooth behavior, but usually is not always. The modern world is full of places where the hidden grain of reality becomes useful. Lasers depend on atoms releasing light in highly controlled quantum transitions. LEDs glow because electrons move between energy states in materials. Magnetic resonance imaging, used in medicine, depends on quantum properties of atomic nuclei. The colors of chemicals, the stability of matter, the behavior of semiconductors, even the fact that atoms can form reliable bonds. All of this belongs to the quantum architecture beneath the smooth surface of life. So when you look at your phone, enter a hospital scanner, see a neon sign, or warm yourself under sunlight, you are already living inside technologies and natural processes that only make sense because reality is not perfectly smooth underneath. The strange part is not that quantum physics lives far away in laboratories. The strange part is that it has been quietly supporting ordinary life the whole time. The chair beneath you feels continuous because electromagnetic forces between atoms resist compression. Your skin never truly touches the chair in the simple way you imagine. The outer electrons of atoms repel, fields interact, and your nervous system translates that resistance into the feeling of contact. The smoothness is an experience, not the full mechanism. And perhaps this is the deeper lesson. Reality often becomes simple only after something more complex has been hidden from view. You do not need to know the atomic structure of glass to drink water from it. You do not need to understand electron energy levels to enjoy the warm color of a lamp. But if you pause long enough, the ordinary begins to glow differently. The world stops being a finished surface and becomes a layered event. Smoothness becomes a mercy, a translation your mind can handle. Quantum physics does not take the world away from you. It adds depth beneath it. It teaches that what feels continuous may be assembled from permitted states, tiny exchanges, stable patterns, and hidden restrictions. It asks you to hold two truths at once. The world of experience is real, but it is not complete. The smoothness you feel is useful, but it is not fundamental. And as that idea settles, even the quietest objects become less plain. A stone is no longer just a stone. It is a vast arrangement of atoms holding their shapes through quantum rules. A color is no longer just a color. It is a message from energy levels too small to see. A surface is no longer just a surface. It is the place where your senses turn microscopic structure into a feeling of simplicity. So the next time the world feels smooth, calm, and continuous, let that comfort remain, but let it become more mysterious. Beneath the stillness, nature is not a blank, unbroken sheet. It is a hidden architecture of allowed patterns, tiny exchanges, and rules so precise that they build the softness of your everyday life from a depth your eyes will never directly enter. Reality seems smooth because you are large, because your senses are gentle, because your brain prefers the flowing story over the invisible steps. But quantum physics leans close and whispers that the river is made of countless secret decisions, and the surface is only the beginning. A particle doesn't choose a path the way you think. What if the smallest traveler in nature never walks the road you picture for it, never moves like a dust grain crossing a beam of sunlight, never quietly follows one hidden route from here to there, but instead reaches its destination through a deeper kind of accounting, where many possible journeys leave their faint influence before the world gives you one visible result? This is one of the hardest habits to break when you first enter quantum physics. The belief that a particle must have a private little path, even when no one is watching. Your mind wants to imagine it like a tiny bead moving through space, turning left or right, passing this point and then that point, carrying a secret history even if you do not know it. That is how ordinary objects behave. A thrown stone follows a curve, a car follows a road, a raindrop falls through the air in a definite way, whether or not anyone sketches its motion. But a quantum particle does not choose a path in that familiar sense. It is not simply a tiny version of a pebble. When it moves between a starting point and an ending point, quantum theory does not describe it as committing to one clean route in the dark. Instead, the theory assigns influence to many possible ways the particle could connect the beginning to the end. Some of those possibilities strengthen the final result, others weaken it. Most cancel out so completely that they never become part of what you later see. And this is where the idea becomes both beautiful and unsettling. The ordinary path we imagine is often not fundamental, but something that emerges after countless microscopic possibilities have quietly balanced one another out. A particle's journey is less like a marble rolling along a groove and more like a soft choir of possible motions, most of them fading into silence, leaving only the patterns that survive together. This does not mean the particle is confused, or magical, or consciously deciding among options. It means our everyday picture of motion is too narrow. In classical life, you can usually say where something was at each moment because the object is large, heavy, constantly interacting with its surroundings, and forced into a stable history. But in the quantum world, before a clear interaction pins down a result, the idea of the path becomes blurry. Not blurry because your instruments are bad, but blurry because nature itself is not offering the same kind of story at that scale. Richard Feynman helped make this idea famous through what is called the path integral approach, though the heart of it can be understood without heavy mathematics. To predict where a quantum particle may be detected, you consider all the possible histories that could connect its start and finish. Each possible history contributes a tiny arrow of influence, a kind of instruction about likelihood. When those influences point together, the result becomes more likely. When they oppose one another, they cancel. What remains is not a diary of where the particle really went in the everyday sense, but a pattern of outcomes nature allows. This is why the straight-looking path of the everyday world can appear from quantum weirdness. For large objects, the wildly different possible routes cancel so efficiently that only the familiar classical route survives strongly. A thrown ball looks as if it follows one path because almost every strange alternative is erased by cancellation, leaving the path of least overall conflict, the one that behaves according to the rules you already know. But for tiny particles, the alternatives can still matter. Their influence has not been washed away. Their possible histories can overlap in ways that change real experimental results. This is not just philosophy. It is why certain quantum predictions work with extraordinary precision. The strange bookkeeping of possible paths helps explain how particles behave in fields, how light and matter interact, and why the microscopic world produces effects no simple hidden road picture can capture. A helpful way to feel this is to imagine trying to walk across a quiet room in darkness, while every possible version of your walk leaves a whisper in the air. One version crosses straight ahead, another curves near the wall, another pauses, loops, and returns. In normal life, that would be nonsense because your body cannot take all those routes. But a quantum particle is not a small body in the same sense. The whispers are not physical copies of it walking around like ghost twins. They are possible histories contributing to the probability of what can happen. That distinction matters. Quantum physics is strange enough without turning it into fantasy. The particle is not literally a tiny person exploring every road with curiosity. It is better to say that nature calculates the final result as though every allowed history has a voice, and the final outcome depends on how those voices combine. When you later see a mark in a detector, it is tempting to draw a line backward and say, that must have been the root. But quantum physics warns you that this backward line may be a story your mind adds after the event. The detector gives you an arrival. It does not always give you a classical journey. This is why particle tracks in devices like cloud chambers can seem both revealing and misleading. In a cloud chamber, you may see a thin trail where a charged particle has passed, and it looks beautifully classical, like a scratch across glass. But that track forms because the particle repeatedly interacts with atoms or molecules in the chamber. Each interaction leaves a local trace, narrowing what can be said next. The path appears through a chain of encounters. It is not necessarily the same as saying the particle had one sharp path before any interaction at all. The track is a history made visible by contact. Without those contacts, the quantum description remains more open, less like a road, and more like a landscape of potential connections. This teaches something important about the word real. We often assume that if something is real, it must have a definite path even when unobserved. But quantum physics separates reality from our preferred kind of description. A quantum process can be real, measurable, and mathematically reliable without being a tiny object following a private classical route. Reality does not disappear. It changes its grammar. Instead of asking, which exact road did it take? Physics often asks, what outcomes are possible? And how do the possible histories combine to make some outcomes more likely than others? That shift is not a weakness. It is the reason the theory works. It lets science predict the behavior of systems that would otherwise seem impossible to understand. It also helps explain why the familiar world returns when things become large. Your own body does not drift through daily life as a visible fog of possible paths, because you are constantly interacting with air, light, surfaces, warmth, and countless surrounding particles. These interactions do not wait politely. They continually narrow possibilities, stabilize records, and make your motion look definite. You experience one path because at your scale, the world is constantly writing the story into the environment. But at the smallest scale, before the story is written, nature is more delicate. It has not yet become the kind of narrative your mind prefers. And maybe this is why the idea feels so quietly powerful. It does not merely say particles are strange. It says a path may not be as basic as you thought. Maybe a path is something that appears when possibilities are filtered, when interactions accumulate, when the world becomes large enough to remember itself. In your life, you often look backward and turn your own history into a single line too. You say, this led to that. I chose this road. Everything followed. But even there, beneath the human story, there were always pressures, near misses, unrealized turns, small influences that cancelled or strengthened one another until one life became visible. The quantum lesson is not that your choices are the same as particles. They are not. It is that the line you see afterward is often simpler than the field of possibility that existed before. A particle does not choose a path the way you think, because nature, at its deepest levels, does not begin with the tidy road. It begins with allowed possibilities, with hidden combinations, with influences that add and erase, until something definite can finally be recorded. And as the thought settles, the world becomes softer around the edges. Motion is no longer just movement from one point to another. It is the emergence of one visible history from a quiet ocean of potential histories. The particle arrives, the detector clicks, the mark appears, and your mind wants the comfort of a road. But quantum physics gently asks you to pause before drawing it. It asks you to let the mystery remain accurate, not exaggerated, not simplified, not turned into magic. The smallest traveler does not move like a tiny stone through invisible space. It moves according to a deeper rule, where many possible ways of becoming leave their trace, and only afterward does reality offer you the calm illusion of a single path. Empty space can change the energy of atoms. Imagine placing an atom inside what you call empty space, removing every speck of dust, every molecule of air, every beam of light you can control until the chamber seems perfectly blank, and then discovering that the atom still feels something there, as if the emptiness around it were not a dead silence, but a soft invisible sea pressing gently on its inner structure. This is one of the quietest and most beautiful surprises in quantum physics. Empty space can change the energy of atoms, not because space is secretly full of ordinary air or hidden heat, or tiny classical particles bumping into things, but because in modern physics, empty does not mean absolutely nothing. It means the lowest possible state of quantum fields, and even that lowest state is not perfectly still. Beneath the calm surface of nothingness, fields retain a kind of restless activity, a minimum trembling that cannot be removed. This is often called vacuum fluctuation, though the phrase can be misleading if you imagine little objects popping in and out like fireflies in a dark room. It is more accurate to think of the vacuum as a background of quantum possibilities that never becomes completely silent. And an atom, delicate as it is, can notice that background. Inside an atom, electrons do not orbit like tiny planets on neat circular tracks. They occupy allowed patterns around the nucleus, each pattern carrying a particular energy. When an electron moves between these patterns, the atom can absorb or release light of very specific colors. For a long time, scientists believed they understood those energies with impressive accuracy. But then experiments with hydrogen, the simplest atom, revealed something strange. Two energy levels that theory first suggested should be the same were not exactly the same. The difference was extremely small, almost unbelievably small, compared with everyday energy. But it was real. It could be measured. This tiny difference became known as the Lamb shift, named after Willis Lamb, whose work helped show that the vacuum itself was subtly affecting the atom. Think about what that means. A nearly empty region of space, stripped down as far as physics allows, changes the internal energy of matter. The atom is not isolated in a blank stage. It is coupled to the invisible fields that fill even the darkest, coldest, most carefully emptied chamber. The electron in hydrogen is electrically charged, and because it is charged, it interacts with the electromagnetic field. Even when no visible light is present, that field still has quantum fluctuations. These fluctuations slightly disturb the electron's behavior, gently shifting the allowed energies of the atom. The result is not dramatic like lightning or explosion. It is a whisper in the spectrum, a minute displacement in the atom's fingerprint. But that whisper was powerful enough to reshape physics. It helped confirm quantum electrodynamics, one of the most successful theories ever created, a theory that explains how light and matter interact with extraordinary precision. What makes this so fascinating is not only the science, but the change in imagination it demands. We usually think objects are affected by what touches them. A hand moves a cup, wind bends grass, heat softens wax. But here, an atom is affected by what seems absent. Space is not pushing in the ordinary sense. No tiny breeze is shaking the atom. Instead, the atom's energy levels are adjusted by its relationship with the quantum fields around it. The emptiness becomes part of the calculation. The background becomes active. The silence has structure. If that feels strange, it should. Your senses evolve to notice solid things, bright things, loud things, moving things. They were not built to notice a tiny correction in the energy of hydrogen. But science often expands the world by revealing influences too small or subtle for the body to feel. The Lamb shift is like finding a faint note in a room you thought was silent, then realizing the note was always there, not from an instrument, but from the nature of the room itself. And once you understand this, the word vacuum changes forever. It no longer means a perfect absence. It means the quietest possible condition of fields that still remain real. Empty space is not a container waiting for matter to arrive. It is part of the physical world, with properties that can shape what matter does. This does not mean empty space is a magical energy source you can freely harvest, and it does not mean atoms are being pushed around by fantasy particles in a cartoon sense. The real story is more restrained and more profound. Quantum fields have ground state behavior. Charged particles interact with those fields. Those interactions slightly alter the energy patterns we observe. The effect is small, but small does not mean unimportant. In fact, some of the deepest truths in physics first appeared as tiny mismatches between prediction and measurement. A small shift in hydrogen became a doorway into a more accurate understanding of reality. It taught scientists that if you ignore the vacuum, you cannot fully understand the atom. It also reminds you that nature does not have to be loud to be fundamental. Sometimes the universe speaks in corrections so fine that only patient instruments can hear them. There is a gentle philosophical weight in this. You live surrounded by what you call empty space, the space between your hand and the wall, between the stars, between the atoms inside your own body. Most of it feels like nothing because nothing obvious stands there. But physics says absence is not always emptiness. The unseen can still participate. The quiet can still shape the visible. The background can still write itself into the behavior of matter. Every atom carries not only its own inner structure, but also the subtle influence of the fields it lives within. And in that sense, no object is completely alone. Even the simplest hydrogen atom is in conversation with the vacuum. It does not float in a mute void. It belongs to a deeper environment, one that remains active even when everything removable has been removed. So the next time you look into a dark room, or stare at the space between two objects, or imagine the vast black distances between stars, try not to picture a dead emptiness. Picture something quieter than quiet, something stripped of ordinary contents but not stripped of reality. The atom knows this before you do. It feels the vacuum in the tiny shift of its energy. It carries the signature of empty space inside its own spectrum. And maybe that is the calm wonder of the quantum world. Even nothing is not simply nothing. Even silence has a texture. Even emptiness, when nature is examined deeply enough, can leave a measurable mark. The smallest things don't have clear edges. What if you could shrink smaller than a dust grain, smaller than a cell, smaller than a molecule, until the familiar world of surfaces and outlines disappeared, and the objects you expected to find as tiny beads with crisp borders began to dissolve into soft regions of possibility instead. At your size, edges feel obvious. A cup ends where the air begins. A stone has a surface. Your hand has skin. A wall has a boundary you cannot pass through. The world seems to be made of things with clear shapes, clear limits, clear outsides and insides. But when you go deep enough into matter, that comforting picture begins to fail. The smallest things do not have edges the way ordinary objects do. An electron is not a little ball with a hard skin. An atom is not a miniature solar system with a neat outer shell like a glass marble. Even the boundary of a proton, one of the particles inside atomic nuclei, is not a sharp line drawn in space. At quantum scales, objects are often described by where they are likely to be found, how they interact, and how their influence spreads, not by a solid surface you could point to and say, "Here it ends." This is one of the most important shifts quantum physics asks you to make. Matter is real, but its smallest pieces are not real in the same shape-based way your senses imagine. Your mind evolved in a world of fruit, stones, animals, tools, and bodies, where edges matter for survival. You need to know where a cliff begins, where food ends, where danger is coming from. But electrons and atoms do not live by the visual language of your daily life. They belong to a deeper layer where edge is often replaced by spread, boundary by probability, and object by behavior. Take the atom. In school, it is often drawn like a tiny nucleus with electrons circling around it in clean loops, as if the atom were a little planet system. That picture is useful only as a first doorway, but it becomes misleading if you hold onto it too tightly. In a real quantum atom, an electron is described by a cloud-like pattern around the nucleus, not because the electron is literally a mist, but because the theory tells us the regions where it is more or less likely to be detected. Some regions are dense with likelihood, others fade gradually. There is no exact outer wall where the atom suddenly stops. The electron's probability can become extremely tiny far away, so tiny that it is practically negligible, but not always cut off like the edge of a table. This means the size of an atom is not like the size of a marble. It depends on how you define it, how the atom is bonded, what other atoms are nearby, and what kind of measurement you use. Chemists can speak meaningfully about atomic radii because those definitions work in practical contexts, especially when atoms form molecules or crystals. But at the deepest level, the edge is not a hard border. It is a fading pattern. It is more like the edge of a fog bank than the edge of a brick. You can say where the fog is thick. You can say where it becomes too thin to matter, but there is no single sharp place where fog suddenly turns into not fog. This is why the smallest things can overlap in ways that ordinary objects cannot. When two atoms come near each other, their electron patterns can interact, merge, repel, rearrange, or form bonds. Chemistry itself depends on the fact that atomic edges are not rigid shells, but flexible quantum regions that can share and respond. The molecules in your body, the structure of DNA, the proteins folding inside cells, the colors of pigments, the behavior of metals and semiconductors, all of them depend on these soft boundaries. If atoms were truly tiny hard spheres with clean edges, the richness of chemistry would be far poorer. Life is possible partly because matter is not as sharply bordered as it looks. Even solidity, the thing that feels most edge-like to you, comes from interactions rather than hard surfaces pressing together like blocks. When your finger touches a table, the atoms in your finger do not simply collide with the atoms in the wood like billiard balls. Their outer electron patterns resist being squeezed into the same states. Electromagnetic forces push back, and your nerves translate that resistance into the feeling of contact. The edge you feel is real as an experience, but it is not a simple meeting of two hard walls. It is a negotiated boundary created by fields, quantum rules, and the structure of matter. Now go even deeper into particles inside the nucleus. You might imagine a proton as a tiny pellet with a definite radius, but modern physics again gives a subtler picture. A proton is made of quarks and gluons, bound by the strong force, and its size is inferred from how other particles scatter from it, or how it affects atomic energy levels. Different experimental methods have even led to careful discussions about exactly how to define and measure the proton's radius. This does not mean the proton is unreal, or that scientists know nothing. It means that at that scale, size is not the same as drawing a circle around a ball. It is a property extracted from interactions. You learn the shape of the small by seeing how it responds when questioned. The clearer your question, the more specific the answer, but the answer is still not always a clean outline. This is also connected to a deeper quantum limit. The more tightly you try to pin down certain aspects of a tiny system, the more other aspects become uncertain. Not because nature is hiding a perfectly sharp object from you, but because the quantum state itself does not always contain the kind of definite information your imagination wants. A small particle can be prepared in a more localized state, yes, but then its motion-related properties become less sharply settled. If you try to make its position too neat, you disturb the calm of its possible motion. Sharpness has a cost. Precision in one sense can create spread in another. This is why the smallest world cannot be understood as a collection of tiny sculpture pieces waiting under a microscope. The very act of making something small and definite changes the conditions of what can be known, and yet this should not make the world feel less real. It should make it feel more alive with structure. A cloud is not unreal because it has no hard edge. A flame is not unreal because its boundary flickers. A melody is not unreal because it exists through pattern rather than solid shape. Quantum objects are similar in a deep way. They are real through their patterns, their interactions, their measurable effects, their stable relationships. The mistake is thinking that reality must look like a miniature version of everyday objects to count as real. The quantum world teaches that form can be softer than outline, and identity can be held by behavior instead of borders. An electron has no known internal structure and no measured size like a little sphere, yet it has charge, mass, spin, and incredibly precise ways of interacting. An atom has no hard outer wall, yet it can form a crystal strong enough to build mountains and bones. A molecule has fuzzy quantum boundaries, yet it can carry the instructions of life. The lack of clear edges does not weaken matter. It allows matter to be subtle. It lets atoms bond, materials conduct, light be absorbed, cells assemble, and the world become textured at the scale you can feel. So when you look at your own hand, you are not seeing a perfectly bordered object in the deepest sense. You are seeing a stable arrangement, a living pattern held together by forces and quantum rules, with boundaries that are practical, useful, and real at your scale, but not absolute all the way down. Your skin marks where your body meets the air, but beneath that visible edge are cells, molecules, atoms, electron regions, fields, and interactions fading into one another with no simple final line. This does not erase you, it makes you more astonishing. You are not a sealed object placed inside the universe. You are a structured concentration of the universe itself, a temporary border drawn by biology, chemistry, and perception. The smallest things do not have clear edges, and maybe that is why the largest meanings do not either. The boundary between object and environment, self and world, solid and empty, is more negotiated than your senses admit. Quantum physics does not say everything is vague in a useless way. It says precision must be earned by asking specific questions. And even then, nature may answer in patterns rather than outlines. In the end, the world you touch remains dependable. The table holds your cup. The floor holds your body. Your hands can build, write, reach, and rest. But beneath that dependable world is a softer foundation, where edges blur, probabilities fade, and matter becomes less like a collection of tiny stones and more like a set of structured possibilities held in delicate balance. And once you know this, even the simplest surface becomes mysterious. The edge of a leaf, the rim of a glass, the outline of your shadow on the floor. All of them are everyday translations of a deeper truth. Nature becomes sharp only when seen from far enough away. Up close, at the smallest scales, reality does not end with a line. It fades, interacts, responds, and only then becomes the solid world you thought you knew. Quantum physics breaks the idea of common sense. What if common sense is not a window into reality, but a set of survival habits your brain learned from objects too large, too slow, and too familiar to reveal what nature is really doing underneath? You trust common sense because it works so well in daily life. A cup stays on the table unless something moves it. A door is either open or closed. A coin is either heads or tails. A sound comes from somewhere. A thing cannot be here and there in any meaningful way. The world seems built from clear objects, stable properties, and causes that march forward in a neat order. This is the kind of world your hands understand. The kind of world your eyes can follow. The kind of world your body needs in order to walk through a room without fear. But quantum physics breaks that confidence, not by making reality meaningless, and not by saying anything can happen, but by showing that the rules beneath ordinary experience are not shaped like ordinary experience. Common sense is local, human-sized, and practical. Quantum physics is microscopic, relational, and precise in ways that feel deeply unnatural. It tells you that a tiny system may not carry a complete list of definite properties before it is tested. It tells you that the outcome of an experiment may be genuinely probabilistic, not merely unknown because you lack information. It tells you that two systems can share a single description even when separated, so that the old idea of completely independent little objects begins to weaken. It tells you that asking one question clearly can make another question harder to answer clearly. And perhaps most unsettling of all, it tells you that nature does not care whether its deepest behavior feels reasonable to a mind trained by falling apples, rolling stones, and familiar shadows. The first mistake common sense makes is assuming that the world must be made of tiny versions of the things we already know. We picture particles like grains of sand, atoms like miniature balls, motion like a path drawn on paper, and measurement like looking through a window. But quantum physics says that these pictures are useful only up to a point. They are mental tools, not final truth. A quantum system is not simply a smaller copy of a pebble. It is described by a state that can contain several possible outcomes at once, not as a vague metaphor, but as a working physical description that predicts experiments with astonishing accuracy. When you measure, you do not merely reveal a hidden answer in the same way you reveal a card already lying face down on a table. In many quantum experiments, the measurement helps define which kind of answer can appear. This is why quantum physics feels like an insult to common sense. It refuses to separate the question from the answer as cleanly as everyday thinking expects. In ordinary life, you believe an object has its properties whether or not you check. The apple has a weight, the clock has a time, the car has a speed. But in quantum physics, some properties do not behave like pre-written labels waiting to be read. They are tied to the experimental setup, to the kind of interaction being performed, to the way the system is allowed to show itself. This does not mean reality is created by imagination. It does not mean your wishes control atoms. It means that at small scales, properties are not always independent possessions of isolated objects. They can be features of a whole situation, system, measuring device, and interaction. Common sense wants the object alone to carry the full story. Quantum physics often says the story belongs to the relationship. Another way common sense fails is with randomness. In daily life, randomness usually means ignorance. If a dice roll surprises you, you still believe that, in principle, the motion of the dice followed ordinary causes. If you knew the exact throw, air currents, surface details, and motion, perhaps you could predict the result. Quantum randomness is different. According to standard quantum theory, some outcomes are not merely hidden from you. They are not fixed in the classical way before the relevant interaction. The theory gives probabilities, and those probabilities are not signs of laziness. They are the best and most accurate description nature gives us. This is difficult to accept because your mind loves hidden certainty. It wants to believe that behind every surprise, there is a secret mechanism with a simple answer. Quantum physics does not fully satisfy that desire. It gives rules that predict patterns with extraordinary success, yet it does not always give the kind of story your intuition asks for. It can tell you the chances with breathtaking precision, but not always the single reason why one individual outcome happened instead of another. That is not a failure of science. It may be a failure of our expectation that explanation must always look like a tiny clockwork machine. Common sense also assumes that separateness is obvious. If two objects are far apart, one should not instantly depend on the other in any deep way. A book on your desk and a stone on the moon seem like separate things. This assumption works beautifully in ordinary life, but quantum physics revealed that when systems interact and become linked, the description of the whole can matter more than the description of the parts. Entangled systems are not well understood as two fully separate objects carrying their own independent instruction sheets. Their measured results can be correlated in ways stronger than classical common sense allows. This does not let us send messages faster than light, and it does not turn the universe into a fantasy of instant communication. The real lesson is more disciplined and more strange. Nature's correlations can be deeper than the local picture our instincts prefer. The world may not be built first from isolated things that later connect. At the quantum level, connection can be part of the basic description, and when you realize that, common sense begins to look less like truth and more like a useful simplification. It is what reality looks like after countless tiny interactions have blurred the deeper rules into the stable world of tables, lamps, bodies, and roads. That stable world is not fake. You can still trust your chair to hold you. You can still pour water, open doors, catch keys, and live by the ordinary rules that experience has taught you. Quantum physics does not destroy everyday reality. It explains why everyday reality is only one layer. The mistake is believing that the layer you live in must be the layer everything is built from. It is like judging the ocean only by the calm surface seen from shore, never imagining the pressure, currents, darkness, and life beneath. Common sense is the shoreline view of reality. Quantum physics is what happens when you dive too deep for familiar instincts to breathe. And yet, there is something strangely peaceful in this. If common sense can break, then certainty does not have to be worshipped. If the universe is deeper than intuition, then confusion is not always a weakness. Sometimes confusion is the honest feeling of the mind stretching beyond the environment that shaped it. A child's common sense says the earth is flat because the ground nearby looks flat. Later, learning reveals a larger truth. In the same way, adult common sense says reality must be definite, separate, and mechanical because daily life appears that way. Quantum physics asks for another growing up of the mind. It asks you to accept that truth may be reliable without being familiar, exact without being picturable, real without being comfortable. And this is where the subject becomes more than physics. It becomes a lesson in humility. Your intuition is not useless, but it is not a king. It is a tool built by evolution, a lantern bright enough for the path in front of your feet, not for the hidden architecture of the cosmos. Quantum physics breaks common sense so that a deeper sense can begin. A sense that reality may be structured by probabilities, relationships, limits, and interactions more subtle than any object you can hold. So when the quantum world feels absurd, do not rush to turn it into magic, and do not flatten it into something familiar too quickly. Let it remain strange in the right way. Let it teach you that the universe is not obligated to match the stories that made survival easy for human beings. The world of common sense is real enough to live in, but not deep enough to end the question. Beneath it, nature is quieter, sharper, and more surprising than your instincts expected. And maybe that is the gift hidden inside the discomfort. Quantum physics does not make reality less trustworthy. It makes your wonder more honest. Matter is not as solid as it feels. Imagine pressing your palm against a wooden table and trusting, without hesitation, that the table is solid because it pushes back, because it holds your weight, because it refuses to let your hand pass through it. And then imagine discovering that this feeling of solidity is not the simple truth of matter, but the final sensation produced by invisible forces, quantum rules, and the restless architecture of atoms. Matter feels solid because your body is large, slow, and built to translate resistance into certainty. The table does not feel like a storm of particles. It does not feel like a structure held together by electric fields. It feels like one firm thing, but beneath that firmness, the story is far stranger. Most of what you call solid is not solid in the way a child might imagine it, like tiny bricks packed perfectly together with no room between them. Atoms are not little blocks stacked edge to edge. They are mostly space in the ordinary sense, with a tiny nucleus at the center and electrons arranged around it in quantum patterns. If an atom were enlarged to the size of a stadium, the nucleus would be like something tiny near the center, while the electron region would extend far outward, not as a hard shell but as a structured zone of influence. And yet, this does not mean matter is empty in a useless or fake way. That common phrase, matter is mostly empty space, is only half the lesson. The deeper truth is that the space inside matter is filled with fields, rules, and restrictions that make objects behave as if they are solid. Your hand does not pass through the table because the charged particles in your hand and the charged particles in the table interact. Their electron structures resist being forced into the same arrangement. Electromagnetic forces push back. Quantum rules prevent electrons from all collapsing into the lowest possible state. This is not a wall made of tiny stones. It is a wall made of relationships. Solidity is not a substance hiding inside matter. It is a behavior that emerges when countless microscopic interactions become organized enough to feel continuous. When you lean on a table, you are not feeling the table's atoms touching your atoms like miniature billiard balls. You are feeling a vast resistance created by electric charge and quantum exclusion, translated by nerves into pressure. Your skin says, there is a surface here, but physics says, there is a powerful refusal of overlapping states here. That refusal is so consistent that your life can depend on it. You can place a glass on a shelf, walk across a floor, sleep on a bed, build a city of steel and stone, and never once feel the hidden weirdness beneath it. But the weirdness is still there. It is there in the way crystals hold shape, in the way metals bend instead of shatter, in the way rubber stretches, in the way glass seems rigid but can fracture suddenly, in the way diamond becomes one of the hardest natural materials, because its carbon atoms are bonded in an extremely strong three-dimensional network. The solidity of each material is not the same kind of solidity. Wood, bone, metal, plastic, ice, and skin all feel solid in daily life, but each one gets that feeling from different microscopic arrangements. In metals, some electrons can move more freely through the structure, which is why metals conduct electricity and heat so well. In ceramics, atoms may be locked into stiff arrangements that resist bending but break under stress. In polymers, long molecular chains can slide, twist, stretch, and return, giving softness or flexibility. So even the word solid hides a whole family of behaviors. A pillow is solid enough to stop your hand from falling through it, but soft enough to deform. Steel is solid enough to hold buildings upright, but under enough force, even steel bends, flows, or breaks. The difference is not magic, it is structure. Matter is not solid as a simple fact. It becomes solid in different ways depending on how its atoms are arranged, how strongly they bond, how freely their electrons move, how temperature makes them vibrate, and how force is applied. Even a rock, which seems still, is alive with microscopic motion. Its atoms are not frozen statues. They vibrate in place, shifting subtly around stable positions. Heat is part of this motion. Warm the rock enough and those vibrations grow stronger. Heat a solid far enough and its structure can loosen into liquid. Heat it more and it becomes gas, where the particles separate widely and move freely. This means solidity is not the permanent identity of a material. It is a phase, a condition, a balance between attractive forces holding particles together and thermal motion trying to pull their order apart. Ice feels firm in your hand, but the same water becomes fluid in a cup, an invisible vapor in the air. The atoms have not become less real. The arrangement has changed. The feeling has changed because the relationships have changed. This is why matter should not be imagined as a collection of perfectly solid little pieces, but as a set of patterns that can organize into firmness, softness, flow, or vapor depending on conditions. At the deepest level, what you call touch is your body encountering one of those patterns and converting it into sensation. There is a quiet humility in that. Your sense of solidity is incredibly useful, but it is not a complete explanation. It is the nervous system's summary of a microscopic negotiation. And the summary is so convincing that you may live your whole life mistaking it for the whole truth. You knock on a door and hear a sound. You step on pavement and feel support. You hold a stone and feel weight. Each experience says, this is solid. But physics adds gently, solid is what organized resistance feels like from the inside of a human body. And when you follow this idea further, it becomes even more astonishing. The same principles that make a table resist your hand also help explain why ordinary matter does not collapse. Electrons cannot all pile into the same state around atomic nuclei. This quantum restriction helps give atoms their size and helps matter keep its structure. Without it, chemistry would not work as you know it. Objects would not hold form. Your body would not have stable molecules. The world would not become a landscape of durable things. In extreme places, this resistance becomes cosmic. White dwarf stars, the dense remains of certain stars, are held up partly by a pressure that comes from electrons resisting being squeezed into identical states. Push matter even further, and in neutron stars, similar quantum ideas involving neutrons help create objects so dense that a spoonful would have unimaginable mass. These are not everyday solids, but they reveal the same deeper lesson. What feels like firmness can come from rules that are not visible, rules about what particles are allowed to do when compressed. The chair beneath you and the corpse of a star are not the same object, but both remind us that matter's resistance is not just mechanical. It is quantum. It is written into the permissions and limits of nature itself. So the next time you rest your hand on a wall, do not think of solidity as something simple and final. Think of it as a song made from forces you cannot hear. Think of your hand and the wall not as two absolute blocks meeting, but as two organized systems refusing to pass through one another because their charges, fields, and quantum rules create a boundary your nerves can understand. That boundary is real, but it is not what it seems. It is not a flat, hard truth at the bottom of the world. It is an emergent feeling, a large-scale result, a dependable illusion in the best sense. Not false, but incomplete. Matter is not as solid as it feels because feeling was never designed to reveal the inner structure of matter. Feeling was designed to help you survive it, and still, there is beauty in that limitation. The table holds, the ground supports, your hand can touch another hand and feel warmth, pressure, presence. The quantum story does not take that away. It deepens it. It says that every touch is a meeting of invisible architectures, every surface a treaty between forces, every solid object a temporary agreement among restless parts. The world remains firm enough to live in, but beneath its firmness is not dead hardness. Beneath it is motion, law, space, charge, and pattern. Beneath it is a universe quietly holding itself together, so convincingly that you call it solid, and so mysteriously that the word will never feel quite simple again. A quantum state can be real without being visible. Imagine holding a sealed letter that changes the world outside it, even though you are not allowed to open it directly, and every time you try, the letter does not simply reveal itself, but becomes part of the very event you used to read it. That is close to the strange status of a quantum state. It can be real, powerful, and necessary for explaining what happens, even when it is not visible in the ordinary sense. In daily life, visibility feels like proof. You see a chair, so you say the chair is there. You see a candle flame, so you trust its light. You see a shadow, a footprint, a crack in glass, and your mind feels satisfied because evidence has taken a shape your senses understand. But quantum physics asks you to separate reality from visibility. A quantum state is not usually something you can look at like a tiny object under a microscope. It is not a glowing label attached to a particle. It is a description of what can be known, what can happen, and how a system is prepared before a particular result appears. And yet, it is not just ignorance. It is not merely a scientist saying, "We do not know what is there." A quantum state carries real structure. It predicts patterns. It decides which outcomes are possible, which are likely, which are impossible, and how the system will respond when different kinds of questions are asked. You may never see the state itself as a picture, but you can see its consequences. The way you never see the wind itself, but watch trees bend, waves wrinkle, and dust drift across the floor. The mistake is thinking that only the final visible result deserves the word real. In the quantum world, the invisible preparation can be just as important as the visible mark. Think of an electron prepared in a certain spin state. Spin is not the same as a little planet rotating, even though the name suggests that image. It is a built-in quantum property that shows up when you test the particle in specific ways. If you send electrons through a device designed to separate them according to spin, you do not see the spin floating in space beforehand. You see where the electron ends up after the interaction. But the state it had before that test matters deeply. Prepare it one way, and the outcomes follow one pattern. Prepare it another way, and the pattern changes. The state was not visible, but it was not meaningless. It was the quiet instruction behind the visible event. The same is true with light. A photon can have a polarization state, meaning its electric field has a certain kind of orientation or combination of orientations. You cannot hold that state in your hand or see it as a colored stripe in the air, but place the photon through polarizing filters and the hidden preparation reveals itself statistically. Some photons pass, some are blocked. Rotate the filter and the outcomes change. The invisible state leaves fingerprints in what becomes visible. This is one of the most important lessons of quantum science. Reality can be known indirectly through repeated patterns, careful preparation, and response to measurement. It does not have to arrive wearing the costume of an everyday object. But there is an even deeper subtlety. A single measurement usually cannot reveal a full quantum state. If you measure one property, you get one answer, and the original state may be changed by the act of measuring. This is why scientists often need many identically prepared systems to reconstruct a state. They prepare the same kind of quantum system again and again, ask different questions, collect many outcomes, and slowly build a picture of what the state must have been. This process is sometimes called quantum state tomography, and the name is fitting. In medical tomography, you do not see the inside of a body all at once. You take many slices, many angles, many signals, and assemble an image from them. In quantum tomography, the image is not a normal photograph, but a reconstructed description of a state that cannot be directly looked at without altering the situation. It is as if nature allows you to understand the invisible, but only through patience, repetition, and humility. The state is real enough to guide outcomes, but too delicate to be simply displayed. This challenges the old habit of believing that reality must be immediately picturable. Some of the most important things in science are not visible in themselves. You do not see gravity as an object. You see falling, orbiting, bending weight. You do not see an electric field directly. You see charges respond. You do not see the rules of genetics with your eyes. You see inheritance, proteins, traits, and patterns in living bodies. A quantum state belongs to this family of hidden structures, but with a sharper twist. It is not just hidden from poor eyesight. It is hidden because measurement in quantum physics is not a passive glance. To measure is to interact, and to interact is often to change the state. So the quantum state lives in a strange space between knowledge and being. Some interpretations treat it as a real physical feature of the world. Others treat it more like information about possible outcomes. Physicists still debate what a quantum state truly is, and that debate is honest, not a weakness. The practical power of the state is undeniable, even when its meaning remains philosophically deep. It is one of the places where science becomes both exact and mysterious at the same time. The equations work, the experiments agree, technologies depend on it. Quantum computing, quantum cryptography, atomic clocks, and precision measurements all rely on controlling quantum states that no one can simply see in the usual sense. A quantum bit, for example, can be prepared in a state that is not merely 0 or 1, but a controlled combination of possibilities. You do not see that combination glowing inside the machine. You manipulate it, protect it, and finally measure it, watching the outcome appear. The invisible state is the resource. The visible result is only the last page of the story. And this is where the idea becomes quietly philosophical. How much of your world do you dismiss because it is not immediately visible? How often do you confuse appearance with existence? A seed before it sprouts does not show the tree. Yet the structure that can become a tree is already there. A musical score is silent on paper, yet it carries a symphony. A sleeping memory is not present in your awareness, yet it can shape a reaction years later. These are not quantum states, but they help your mind soften toward the lesson. Invisibility does not mean emptiness. Some realities announce themselves only through what they make possible. In quantum physics, a state can be real because it constrains the future, because it shapes probabilities, because it responds consistently to different experimental questions, because it can be prepared, transformed, protected, and used. It does not need to be visible like a stone on a table. It is real in the way a pattern is real before it becomes a picture, in the way a rule is real before it becomes an event, in the way a possibility can have structure before it becomes a fact. So when you imagine the quantum world, do not picture tiny things hiding behind a curtain, waiting to be seen clearly if only your microscope were strong enough. Picture a deeper layer where states are delicate arrangements of potential behavior, where the unseen is not vague but ordered, where the invisible can guide the visible with extraordinary precision. A quantum state can be real without being visible because reality is not limited to what the eye can catch. Sometimes reality is the preparation behind the result, the pattern behind the event, the silent condition that decides what kind of answer nature can give. And in that quiet realization, the world grows wider. You learn that seeing is not the highest form of knowing. Sometimes the most real thing in the room is not what appears, but what makes appearance possible. Particles can act like events, not objects. What if a particle is not a tiny object traveling through the universe, but a moment when the universe briefly becomes countable, measurable, and able to leave a trace? That thought sounds strange because your everyday mind is trained to understand reality through objects. You see a book, a chair, a cup, a stone, and each one seems to be a thing that continues to exist quietly when you stop paying attention. It has a shape, a position, a history. It can be moved, dropped, broken, or held. So when physics talks about particles, it is natural to imagine smaller versions of those objects. Little grains of matter, tiny dots flying through space, invisible beads making up everything around you. But modern quantum physics slowly teaches a different picture. At the deepest levels, what we call a particle is often better understood through what happens, not through what sits there. A particle is known by an interaction. It is created in one event, detected in another, transformed in another, absorbed in another. You do not usually meet it as a tiny solid thing with a clear personal identity. You meet it through evidence, a flash in a detector, a click in an instrument, a track in a chamber, a small deposit of energy, a pattern that repeats after thousands or millions of trials. In this sense, particles are less like permanent miniature objects and more like reliable ways nature can make events occur. This does not mean particles are imaginary. It means their reality is not the same kind of reality as a pebble in your hand. A pebble is a large, stable arrangement of many atoms that keeps its form because countless internal interactions hold it together. A particle, especially in high-energy physics, may exist only briefly, sometimes for such a tiny fraction of time that it cannot be seen directly at all. Scientists know it was there because of what it produced, how it decayed, how energy and momentum were distributed afterward, and how the result matched a precise prediction. The particle is real because the event pattern is real. Think of thunder. You do not hold thunder like an object. It is an event in the air, a sudden pressure wave caused by lightning. Yet thunder is not fake because it passes. A flame is similar. It can look like an object because it has shape, color, and location, but a flame is actually a continuing process, a chemical event sustained by fuel, oxygen, and heat. Stop the process and the thing disappears. Many particles, especially unstable ones, are closer to this than to marbles. They are temporary excitations, brief organized appearances in underlying fields. Quantum field theory, the framework behind much of modern particle physics, tells us that fields are fundamental, spread throughout space, and particles are excited states of those fields. The electron field can produce electrons. The electromagnetic field can produce photons. Other fields correspond to other particles. This is not just a poetic idea. It is the language that allows physicists to predict experiments with extraordinary accuracy. In that view, the universe is not primarily a container full of tiny objects. It is more like an invisible ocean of fields, and particles are the ripples, pulses, or localized disturbances that can be created, exchanged, and detected. But even those comparisons are imperfect, because a quantum field is not water, and a particle is not a little splash you can watch with ordinary eyes. The comparison only helps you loosen the old object picture. What matters is this: particles reveal themselves through interactions. Without interaction, there is often no visible story to tell. A neutrino is a perfect example. Neutrinos are incredibly common, produced by the sun, nuclear reactions, and cosmic events, and enormous numbers pass through your body every second. Yet they almost never interact with you. They pass through Earth as if the whole planet were nearly transparent. If reality were only what you could feel, you would never suspect them. But in huge underground detectors, once in a while, a neutrino interacts with matter and creates a faint signal. That rare event is how the invisible becomes scientifically real. The neutrino is not accepted because someone imagined it dramatically. It is accepted because its events match a structure of evidence. Another example is the Higgs boson. It was not found sitting like a speck under a cosmic microscope. It appeared through collision events in particle accelerators, where high-energy interactions produced patterns that could not be explained without it. The Higgs boson decayed almost instantly, and scientists reconstructed its presence from the particles left behind. So, the particle was known as a moment in a chain of happenings, not as a durable object waiting to be photographed. This event-like nature also changes how you think about identity. In ordinary life, you can ask whether the same coin is still in your pocket. With quantum particles of the same type, individuality becomes less familiar. One electron is not different from another electron in the way one coin differs from another. Electrons are identical in their basic properties. If two electrons switch places in a calculation, nature does not treat them as two labeled objects with private names. This indistinguishability is not a small detail. It helps explain the structure of atoms, the behavior of matter, and the reason chemistry has the patterns it does. Again, the old object picture weakens. The universe does not seem to care about tiny personal labels attached to particles. It cares about states, interactions, allowed arrangements, and measurable outcomes. A particle's being is tied to the role it plays in the whole physical situation. That is why physicists often describe particle behavior through probabilities, conservation laws, and interaction rules, rather than through little stories about tiny travelers. Energy must balance. Momentum must balance. Charge must be conserved. Some transformations can happen, others cannot. These rules define what events nature permits, and out of those permitted events, the visible world eventually forms. Your body, your room, the ground beneath you, the stars above you, all of them are stable, large-scale results of innumerable small interactions. The world feels like a collection of objects because the events are organized, repeated, and woven together so densely that they appear continuous. Like a film made of frames or a song made of notes, the flow becomes smooth enough that you forget the pieces. But quantum physics invites you to remember the pieces without reducing the beauty. It says the universe is not just made of things. It is made of happenings that become things when they are stable enough to persist. This is a powerful shift because it teaches that existence may be more active than it looks. A particle is not always a tiny noun. Sometimes it is closer to a verb. It is not only something that is, it is something that occurs, interacts, transforms, and leaves a trace. And perhaps this is why the quantum world feels so difficult to picture. Your imagination wants furniture, but nature gives you processes. Your imagination wants little solid actors on a stage, but nature gives you fields, excitations, transitions, and records. The particle is the visible word printed at the end of a sentence whose grammar is deeper than sight. So when you hear that particles can act like events, not objects, do not take it as a denial of reality. Take it as a more careful definition of reality. The smallest things are real because they participate in events that can be measured, predicted, and repeated. They are real because they carry energy, charge, momentum, and influence. They are real because detectors respond, atoms change, light is emitted, and patterns appear. But they are not always real in the old simple way your hands expect. They do not always sit in the universe like tiny stones waiting to be found. Sometimes they are the universe briefly expressing a possibility as an occurrence. And once you understand this, the world around you begins to feel less like a warehouse of silent objects and more like a calm surface above endless activity. Every lamp, every breath, every heartbeat, every reflection is built from events so small and numerous that they become the steady furniture of your life. The object is what your senses receive after the happening has become stable. The event is the deep emotion beneath the name, and maybe that is the quiet lesson hiding here. Reality is not only what remains. Reality is also what happens. The universe may be built from probabilities, not certainties. Imagine waking up in a universe where the future is not written in ink, not waiting behind the next second like a sealed page, but held as a set of weighted possibilities, each one real enough to matter. None of them guaranteed until nature finally gives an answer. This is the quiet shock behind quantum physics. The universe may be built not from certainties, but from probabilities. In everyday life, probability often feels like weakness. You say there is a chance of rain because you do not know enough about the weather. You say a coin might land heads or tails because you cannot track every tiny motion of the toss. You say someone may arrive late because you lack full knowledge of traffic, timing, and choice. In that ordinary sense, probability is a mask over ignorance. It means the truth is already decided somewhere, and you simply do not have access to it yet. But quantum physics introduces a more radical kind of probability, one that does not merely describe what you fail to know, but seems to describe what nature itself is willing to say before an outcome occurs. A radioactive atom, for example, does not come with a visible countdown clock showing the exact instant it will decay. If you place one unstable atom in a detector, physics can tell you the chance that it will decay within a certain time, and that prediction can be tested with extraordinary precision across many atoms. But for the single atom, standard quantum theory does not give a hidden appointment time. It gives a probability. One atom may decay almost immediately. Another identical atom may remain unchanged much longer. Nothing in the usual quantum description says, this exact one must decay at this exact moment. And yet, when you gather many atoms together, an astonishing order appears. Half-lives become reliable, patterns become stable. The group behaves with mathematical discipline, even while each individual event carries irreducible uncertainty. This is not chaos. It is not nature being careless. It is probability with structure, uncertainty with law. The universe does not simply shrug and throw outcomes around randomly. It assigns chances in precise ways, and those chances shape the visible world. That is what makes quantum probability so different from ordinary guessing. It is not a failure to predict. It is the form prediction takes at the deepest level we know. You can see this in how physicists speak about where a particle may be found, how likely a transition is, how often a detector should click, how a system will behave after many repeated trials. The language is not, here is exactly what must happen every time. The language is, here is the distribution of what can happen, and here is how often each result should appear. At first, that may feel less satisfying than certainty. Your mind wants a single hidden script. It wants the universe to be a machine whose future would be perfectly knowable if only you had a powerful enough mind. That dream belonged to classical physics for a long time. The idea that if you knew every position, every motion, every force, then the future could be calculated like the next line in a poem already written. Quantum physics did not simply add blur to that picture. It changed the picture. It suggested that at small scales, reality does not always contain the kind of definite future that classical imagination expects. Before certain events happen, nature may not be holding one fixed answer behind the curtain. It may be holding a set of possible answers, each with a weight. When the event occurs, one result becomes actual, but the pattern of many such results reveals the probability rule underneath. This is where the famous Born rule enters. Though you do not need its mathematical symbols to feel its meaning. It is the rule that connects the quantum description of a system to the probabilities of outcomes we can observe. Without it, the quantum state would be like a silent map with no legend. With it, scientists can turn the hidden structure of possibility into testable predictions. And those predictions are not vague. They are among the most successful in all of science. Quantum probability helps explain the behavior of atoms, the light emitted by elements, the operation of lasers, the stability of materials, the timing of radioactive processes, and the foundations of modern electronics. The world you live in is not less dependable because probability lies beneath it. In a strange way, it is dependable because probability follows rules. If every microscopic event were certain in the old classical way, the universe would be easier for intuition, perhaps, but it would not be the universe experiments show us. And if every microscopic event were pure disorder, there would be no atoms, no chemistry, no stars, no bodies, no memory, no science. What exists instead is something more subtle, a reality where individual outcomes may not be fixed in advance, yet large-scale patterns become stable enough to build a world. Think of a city at night seen from far above. You cannot know exactly which window will turn off next. Which person will step into which street? Which car will stop at which corner? But the city as a whole has rhythms. Morning traffic rises. Lights gather in certain districts. Crowds move with patterns. Individual uncertainty does not prevent collective order. Quantum physics is deeper and stricter than that image, but it points toward the same emotional truth. Certainty at the large scale can emerge from probability at the small scale. This is why your everyday world does not feel like a storm of chances. The probabilities average, combine, and stabilize through enormous numbers of interactions. A single quantum event may be unpredictable, but a trillion events can produce the regular world your senses trust. The warmth of sunlight on your skin, the glow of a screen, the decay used in medical imaging, the behavior of electrons in a chip. All of these depend on probabilistic rules becoming reliable through repetition. There is humility in this. The universe may not be a book where every letter of the future is already printed. It may be more like a score where possibilities are written with different strengths, and the performance becomes real note by note. You are not meant to imagine that anything can happen in a lazy or mystical way. Most things cannot happen. Nature is strict. The possible outcomes are limited. Their chances are shaped by the system's preparation and the laws that govern it. But within those limits, certainty gives way to likelihood. And that opens a different kind of wonder. It means the future is not merely hidden from you. In some situations, it may be genuinely open until the physical event occurs. It means reality is not always a finished object waiting to be uncovered, but a process in which potential becomes fact according to rules that are exact but not fully deterministic. This can feel unsettling because certainty comforts the mind. Certainty says the world is already decided, that every moment is only the unfolding of a perfect mechanism. Probability says something softer and stranger. The world has structure, but not always a predetermined sentence. It has law, but not always a single pre-written outcome. And maybe that is why quantum physics continues to feel so alive. It does not remove order. It removes the old kind of guarantee. It asks you to trust patterns without demanding that every individual event carry a hidden classical reason. So the next time you think of reality as firm, fixed, and already settled, imagine the quiet interior of an unstable atom, the patient detector nearby, the unknown moment waiting without a clock. Nothing dramatic happens for a while. Then suddenly there is an event. Not because your ignorance was finally corrected, but because possibility has become outcome. One mark appears, then another, then thousands more, and from them a law rises. The universe may be built from probabilities, not certainties, but those probabilities are not empty guesses. They are the deep grammar of becoming, the way nature holds the future gently before choosing one present at a time. Probability amplitudes are stranger than ordinary chance. What if chance in the quantum world is not like drawing a card from a shuffled deck, but like listening to invisible waves of possibility that can strengthen each other, weaken each other, or disappear together before anything finally happens? In ordinary life, chance feels simple enough. If there is a small chance of rain, that chance adds to other weather clues. If a dice has 6 sides, each side has its own possibility. If you buy more lottery tickets, your chance increases because you have added more ways to win. Ordinary probability behaves like counting. This many options, this much likelihood, this result more common than that one. It is the language of uncertain outcomes when the outcomes themselves seem plain. But quantum physics hides a stranger layer underneath probability, a layer called probability amplitudes. The name may sound technical, but the idea is deeply important. Before quantum physics gives you an ordinary probability, it first uses something more delicate, something that behaves less like a number written on a betting slip and more like a tiny direction, a rhythm, a rotating instruction, a hidden wave-like contribution. These amplitudes are not the final chances you observe. They are the ingredients from which chances are made. And this is where the strangeness begins, because ordinary probabilities can only add up positively. A 20% chance and a 30% chance do not cancel into nothing. They simply combine according to the rules of ordinary uncertainty. But quantum amplitudes can oppose one another. They can carry a kind of phase, a hidden orientation, like 2 quiet signals arriving out of step. When they align, an outcome can become more likely. When they oppose, an outcome can become less likely, even impossible. Not because nature forgot to include it, but because the underlying amplitudes cancel before probability is born. This is the difference between ordinary chance and quantum chance. Ordinary chance is what you get after the world has already become a list of outcomes. Probability amplitude is part of the deeper machinery that decides how strong each possible outcome will be before it becomes visible. Imagine two paths leading to the same final result. But instead of each path simply adding more likelihood, each path brings a small, invisible arrow. If the arrows point in the same direction, they reinforce. If they point in opposite directions, they cancel. The result is not just more paths means more chance. Sometimes more possible ways can reduce the chance. Sometimes an outcome that seems perfectly allowed can vanish because the amplitudes leading to it erase one another. This is why quantum physics feels so different from rolling dice. With dice, each possible roll is separate. The chance of rolling a 2 does not interfere with the chance of rolling a 5. They do not whisper to each other before the dice lands. But in quantum systems, alternatives can combine before the final outcome, and that combination can change what appears. This is the hidden reason behind interference patterns, behind the sharp, dark places where something could have arrived but does not, behind the strange accuracy of quantum predictions. The universe does not begin by assigning ordinary chances directly. It first lets amplitudes combine, and only after that does the familiar probability emerge. This is one reason quantum theory is so precise and so difficult to picture. You cannot treat its possibilities like colored balls in a bag. A quantum possibility has more structure than an ordinary possibility. It has strength, yes, but also phase, a kind of internal timing or direction that decides how it combines with other possibilities. You do not need heavy symbols to understand the emotional shape of this. Think of sound. Two quiet tones can meet and grow louder if their peaks arrive together. The same two tones can also meet and produce silence if one rises while the other falls. Nothing mystical has happened. The waves have combined according to their structure. Quantum amplitudes work with a similar spirit, though they are not ordinary sound waves in air. They are abstract features of the quantum description, and their cancellations and reinforcements become real in the statistics of experiments. That abstraction is important. A probability amplitude is not usually something you see glowing in space. It is not a tiny physical thread. It is part of the mathematical description that tells us how a system can produce outcomes. Yet it is not empty bookkeeping either, because without amplitudes, the predictions fail. Their phases matter. Their combinations matter. Their cancellations show up in laboratories. They are invisible, but they are not optional. In fact, some of the deepest quantum effects come from the fact that amplitudes are stranger than probabilities. In ordinary probability, if two routes can lead to the same result, and you do not know which route happened, you usually add the chances. In quantum physics, if the alternatives remain capable of interfering, you add amplitudes first, and that can produce results no ordinary chance system could imitate. Only when the alternatives are forced into distinct records, when the environment or a measuring device separates them so clearly that they can no longer interfere, do they begin to behave more like ordinary probabilities. This is one of the quiet bridges between the quantum world and your familiar world. Your daily life feels classical because the delicate phases of amplitudes are usually destroyed or scattered into the environment far too quickly for you to notice. The hidden arrows lose their coordinated relationship. The strange cancellations disappear. What remains is the ordinary world of chances, causes, and stable outcomes. But in carefully isolated quantum systems, the amplitudes can keep their relationships, and then nature reveals its deeper arithmetic. This has practical power, not just philosophical beauty. Quantum computers, for example, do not work by simply trying every answer like a magical machine. A more honest way to understand them is that they try to arrange amplitudes, so wrong answers tend to cancel, and useful answers become more likely to appear. That is an incredibly delicate task, and it only works for certain kinds of problems, under strict conditions, with enormous engineering challenges. But the basic idea shows why amplitudes matter. They are not just a strange footnote. They are a resource. They allow quantum systems to process possibility in a way ordinary probability cannot. Still, You should not turn this into fantasy. Probability amplitudes do not mean your thoughts can cancel reality, and they do not mean the universe is making wishes. They are part of a disciplined physical theory. They follow strict rules. They make predictions that can be tested. Their strangeness is not an excuse to say anything. It is a demand to be more precise about what chance really means. The deeper lesson is that uncertainty is not always simple ignorance. Sometimes uncertainty has structure before it becomes outcome. Sometimes the possible is not just a list, but a pattern. And sometimes two ways something could happen do not merely compete. They combine, interfere, and reshape the final world. This should change the way you hear the word chance. It is not always a loose fog around knowledge. In quantum physics, chance can be built from hidden order, from amplitudes that move like silent instructions beneath visible events. By the time you see a result, the delicate work has already happened. The amplitudes have aligned or cancelled. The possible outcomes have been weighted by a deeper rhythm. The final probability is only the surface. Beneath it is a kind of invisible choreography, precise enough to build lasers, explain atomic behavior, guide quantum technologies, and challenge the oldest instinct that chance is merely randomness. So when you think of probability amplitudes, do not picture ordinary odds wearing a more complicated name. Picture a deeper layer where possibilities have direction, timing, and relationship, where alternatives can erase each other before they ever become facts, where the universe prepares its outcomes through a quiet mathematics stranger than guessing and more orderly than luck. Ordinary chance tells you what might happen. Probability amplitudes whisper how the possible world arranges itself before one answer finally rises into view. Quantum phases can cancel reality out. Imagine two invisible clocks inside nature, both ticking toward the same possible outcome, but one arrives with its hand pointing upward, while the other arrives pointing downward, and instead of making the outcome stronger, they erase it so completely that something which seemed possible becomes absent, not because it was forbidden, but because the hidden timing of possibility cancelled it away. This is the strange power of quantum phase. At first, phase sounds like a small technical detail, the kind of word that belongs only in laboratories or textbooks, but it carries one of the deepest lessons in quantum physics. Possibilities are not all identical. They do not simply sit there as neutral chances waiting to be counted. Each quantum possibility has a kind of internal rhythm, an orientation in the deeper structure of the quantum state. And when different possibilities meet, their phases decide whether they cooperate or destroy each other. In ordinary life, if two roads lead to the same place, you expect the destination to become easier to reach. More roads means more chances, more ways means more likelihood. But quantum physics breaks that simple idea. Two possible ways for something to happen can combine in such a way that the final outcome becomes less likely, or even disappears from the experiment entirely. This is not a metaphor for disappointment. It is a real physical effect. It is why quantum interference can create dark regions, where particles rarely or never appear, even though nothing obvious is blocking them. It is why light passing through certain arrangements produces brightness in some places and darkness in others. It is why electrons in atoms settle into patterns that are not random clouds, but structured shapes, with regions where the chance of finding the electron is high, and other regions where the chance drops because the quantum waves cancel. Phase is the quiet organizer beneath the visible result. It tells the possible paths whether to add their voices or silence each other. A good way to feel it is to think of ocean waves meeting. When the crest of one wave meets the crest of another, the water rises higher. When the crest of one meets the trough of another, the surface can flatten. Nothing has vanished in a magical sense. The motions have combined according to their timing. Quantum phases work with a similar spirit, though they are not ordinary water waves moving through the sea. They are part of the quantum description, and their cancellations appear as real changes in what detectors record. This is where the phrase "cancel reality out" becomes powerful, but it must be understood carefully. Quantum phase does not cancel the entire universe. It does not make objects vanish because someone thinks about them. It cancels specific possible outcomes in specific physical situations. A particle that might have been detected in a certain place may become extremely unlikely there because the contributing quantum possibilities arrive out of phase. An atomic transition that might seem possible from a simple viewpoint may be weakened or prevented because the underlying quantum contributions interfere destructively. A beam of particles sent through a carefully designed experiment may form a pattern of allowed and suppressed results, not because the apparatus is secretly choosing, but because the phases of the quantum state are being shaped. This is one reason quantum physics is so much more than randomness. If it were only random, you would expect scattered noise. Instead, you get patterns with silence built into them. You get absences that mean something. You get dark bands, forbidden directions, missing outcomes, and stable structures, all produced by the way phases line up or oppose. In that sense, absence becomes evidence. A place where nothing appears can be as informative as a place where something appears. The dark stripe on a screen is not empty of meaning. It is the footprint of cancellation. It is nature saying, these possibilities met here, but they erased the result. And this hidden cancellation is not limited to one famous experiment. It runs through the architecture of matter. In atoms and molecules, quantum phases help determine which arrangements are stable, which bonds can form, and how electrons occupy space around nuclei. The shapes of chemical orbitals, the way molecules absorb light, the behavior of materials, and even the colors and conductivity of substances all depend on the wave-like structure of quantum states, including phase relationships. In modern technology, phase is not just a curiosity. Lasers depend on waves of light being coordinated in phase, so they reinforce instead of washing out. Electron microscopes, quantum sensors, interferometers used to measure tiny changes, and many proposed quantum computing methods all rely on controlling phase with extreme care. A tiny disturbance from heat, vibration, or the surrounding environment can scramble phase relationships, and once that happens, the delicate interference disappears. This is why quantum systems are so hard to protect. Their power comes from maintaining a hidden order that the ordinary world constantly tries to blur. Phase is like the timing between dancers in a dark room. If they move together, a shape appears. If they fall out of step, the shape dissolves. And yet, the most haunting part is that phase itself is usually not something you directly see. You infer it from what happens when possibilities are allowed to meet. You do not look at a particle and see a colored tag saying what its phase is. You see the results of phase through interference, through reinforcement, through cancellation, through patterns that cannot be explained by simple chance alone. This teaches a very subtle lesson about reality. What becomes visible is shaped by relationships that may remain hidden. The final outcome is not just determined by how strong each possibility is, but by how those possibilities are arranged relative to each other. Strength alone is not enough. Timing matters. Relationship matters. Alignment matters. Two strong possibilities can produce almost nothing if they oppose each other. Two faint possibilities can become powerful if they move together. That is a strange and beautiful rule to find at the bottom of matter. It means the universe is not only made of quantities, but of relations. Not only of how much, but of how things fit together. This is why quantum phase feels almost musical. A single note has a sound, but harmony depends on relation. Two notes can create peace or tension depending on how they meet. Silence can be composed as deliberately as sound. In quantum physics, reality also has this hidden musical quality. Outcomes arise not just from possible events, but from the phase relations among them. Some outcomes are amplified like a chord resolving. Others are cancelled like noise removed by an opposite wave. And from that invisible composition, the world gains its structure. So when you hear that quantum phases can cancel reality out, do not imagine reality becoming unreal in a dramatic, magical way. Imagine instead a precise and delicate process where nature allows several possible contributions to approach the same result, and their inner rhythms decide whether that result will appear. Sometimes they support each other, and the event becomes likely. Sometimes they oppose each other, and the event fades into absence. What you finally observe is not merely what was possible, but what survived the hidden meeting of possibilities. That is the quiet wonder here. Reality is not only built from what happens, it is also shaped by what almost happened, what could have happened, and what cancelled before it ever reached the surface. The visible world is full of presences, but quantum physics teaches you to respect the absences too, because some of them are not empty at all. They are the places where possibility met possibility and left behind silence. Light can interfere with itself. One photon at a time. What if a single photon could enter an experiment alone, with no partner beside it, no crowd around it, no second wave to collide with, and still leave behind evidence that it has somehow interfered with itself? This is where light becomes deeply unsettling in the gentlest possible way, because your everyday intuition says interference should require at least two things. Two water waves meet and form ripples. Two sound waves overlap and create louder or quieter tones. Two beams of light can combine and produce bright and dark bands. But quantum physics asks you to imagine something far stranger. Send light so weakly that only one photon is moving through the apparatus at a time, and the interference pattern still appears, not instantly, not as a full picture at once, but slowly, patiently, dot by dot, as if each lonely photon participates in a pattern larger than its own arrival. At first the screen looks random. One tiny mark appears here, another there, then another somewhere else. If you stopped after a few photons, you might think nothing meaningful was happening. But if you continue, allowing thousands, then millions of photons to pass one at a time, the dots begin to gather into familiar bands of brightness and darkness. No photon lands as a spread-out smear. Each one is detected as a single localized event. Yet the full collection refuses to behave like simple particles thrown independently through space. The final image carries the signature of wave interference, and because the photons were sent one at a time, you cannot easily say that one photon interfered with another. The pattern seems to come from the quantum description of each photon itself, from the way its possible alternatives remain coherent enough to combine before detection. This is the careful, truthful wonder. A single photon does not split into two tiny half-photons like a broken bead, and it does not literally become two classical objects sneaking through both openings. Rather, the state of the photon can include different possible alternatives, and those alternatives can interfere. The photon is detected once, but the probability of where it will be detected is shaped by the whole experimental arrangement. That is why the dark regions stay dark over time. If the photons were merely little pellets choosing one route or another in an ordinary hidden way, the screen would fill differently. But the experiment shows something subtler. The photon's final landing place is not chosen from a simple map of two independent routes. It is guided by a quantum pattern that includes how the alternatives relate to one another. This is why single photon interference is so important. It removes the easy escape of saying, of course there is interference. Many photons are just bumping their waves together. No, the experiment can be arranged so that the average spacing between photons is so large that only one is inside the apparatus at a time. Still, the pattern returns. The loneliness of the photon does not erase the wave-like structure of its possibilities. A powerful example uses a device called an interferometer, where a single photon meets a beam splitter. A beam splitter is a special optical element that gives the photon two possible paths, like two arms of a very delicate maze. If the paths are later brought back together without revealing which path the photon took, the outcomes at the detectors depend on interference. One detector may click often, while another may remain silent, not because the silent detector is broken, but because the probability for that outcome has been cancelled by the relation between the two possible paths. Change the length of one path slightly, or shift the phase, and the clicking pattern changes. This is astonishing because the photon is still detected as one whole unit. It does not give half its energy to one detector and half to another. It arrives completely in one place. But before that arrival, the possible paths have combined in a way that changes where the complete photon is likely to appear. The experiment teaches that one does not always mean simple. One photon can carry a quantum state rich enough to produce interference. One event on a screen can be part of a pattern that only becomes visible through repetition. One tiny mark can look meaningless until time gathers many marks into structure. And this is where science becomes almost meditative. A single photon never shows you the whole truth. It gives only one answer. But a long sequence of single photons reveals the law underneath. Nature does not display the pattern all at once. It lets the pattern emerge through patience. That is one reason quantum experiments feel so different from ordinary demonstrations. You cannot demand that one photon draw the full interference image for you. You must prepare the same situation again and again, and let many individual outcomes speak collectively. Each photon lands alone, but not lawlessly. Each mark is individual, but the growing pattern is disciplined. This is not the universe being random in a careless way. It is the universe using probability with hidden structure. The deepest surprise is that information changes the behavior. If the experiment is arranged so that the photon's path can be known, even in principle, the interference disappears. The pattern changes from wave-like bands into a distribution more like separate alternatives. But if the path information is erased or never made available, interference can return. This does not mean human consciousness must stare at the experiment. It means the physical availability of path information matters. If the world has a record of which path occurred, the alternatives no longer combine in the same way. If no such record exists, the alternatives can remain part of one coherent quantum story. In simple words, quantum interference depends on whether nature has kept the possibilities together or separated them into distinct histories. That distinction is delicate, and it is the reason quantum systems are so easily disturbed. A tiny leak of information into the environment can ruin the interference. A stray interaction, a vibration, a bit of heat, an uncontrolled measurement can scatter the fragile relationship between alternatives. This is why single photon interference is not just a beautiful mystery, but a practical foundation for technologies such as quantum communication, precision measurement, and experiments testing the deepest rules of reality. Scientists can use individual photons because they are clean carriers of quantum information. Their ability to interfere with themselves, when kept coherent, becomes a tool, not just a puzzle. But beyond the laboratory, the lesson reaches into the way you think about evidence. A single result rarely tells the full story. One photon on a screen is only a point. Many points gathered under controlled conditions reveal a hidden order. In life too, the mind often rushes to judge from one mark, one moment, one outcome, forgetting that some truths only emerge through patterns. Quantum physics does not ask you to abandon reason. It asks you to become more patient with what reason can reveal. It asks you to see that reality may have layers where the individual event and the larger pattern are both true, even when they seem to belong to different worlds. Light can interfere with itself, one photon at a time, because a photon is not merely a tiny object with a single ordinary story before it lands. It is a quantum system whose possible alternatives can remain connected until detection gives one final result. And when enough of those final results accumulate, the invisible structure becomes visible. So imagine the dark screen again, waiting in silence. One dot appears, then another, then another. For a while, nothing seems certain. But slowly, like stars forming constellations in a black sky, the hidden pattern begins to show itself. Each photon arrives alone, yet the universe remembers the whole arrangement. Each event is small, yet the order behind it is vast. And in that quiet accumulation of light, quantum physics offers one of its most honest teachings. The world may reveal itself not in a single answer, but in the pattern left behind by many fragile possibilities becoming real, one at a time. Matter waves make particles behave like ripples. Imagine a grain of matter so small that, when it moves, it does not simply travel like a tiny speck through space, but spreads its presence like a ripple across an invisible pond, carrying with it a wavelength so real that crystals, microscopes, and experiments can reveal its hidden pattern. This is the strange idea of matter waves, the discovery that particles of matter, not just light, can behave in ways that resemble waves. At first, this sounds impossible because matter feels like the opposite of a wave. A stone is here, not gently spread across a room. A grain of dust lands in one place, not across many. Your body does not flow through a doorway like a sound wave bending around a corner. Matter seems firm, located, definite, and heavy. Waves seem extended, flexible, able to overlap and bend. But quantum physics tells us that this separation is not fundamental. In 1924, Louis de Broglie proposed something beautifully simple and deeply radical. If light, which had long been understood as a wave, can also behave like particles called photons, then perhaps particles of matter can also have wave-like properties. Not because an electron becomes water, or because a proton secretly wiggles like a rope, but because every moving particle has an associated wavelength, a hidden wave character connected to its motion. The smaller and lighter the particle, the easier this wave nature is to notice. The larger and heavier the object, the shorter and more impossible to detect its wavelength becomes. That is why you do not see a thrown ball diffract around a doorway, but you can see electrons diffract when they pass through the tiny regular structure of a crystal. The wave nature is not absent from larger things in principle. It is simply so unimaginably tiny and overwhelmed by ordinary interactions that it disappears from practical experience. For electrons, however, the wavelength can be large enough, compared with atomic spacings, to produce real effects. And this was not just a poetic guess. A few years after de Broglie's proposal, experiments showed that electrons could scatter from crystals in patterns like waves reflecting from a repeating structure. The Davison-Germer experiment became one of the great confirmations that matter has wave-like behavior. Electrons fired at a nickel crystal did not scatter randomly, like little pellets bouncing off a rough wall. They produced peaks of intensity at specific angles, the kind of pattern expected when waves interfere after reflecting from regularly spaced atoms. Matter had revealed its ripple side. This changed the meaning of a particle. An electron could no longer be understood only as a tiny point object, moving in a tiny classical path. Its motion had a wavelength. Its behavior could be shaped by interference, diffraction, and the geometry of the environment. And that wave nature became more than a mystery. It became a tool. Electron microscopes work partly because electrons can have much shorter wavelengths than visible light. Shorter wavelength means the ability to resolve smaller details. This is why electron microscopes can reveal structures far too tiny for ordinary light microscopes to see clearly. Cell surfaces, viruses, crystal defects, nanomaterials, and the delicate architecture of the microscopic world. The fact that matter behaves like ripples is not only a philosophical shock, it is built into technology that lets human beings look deeper into matter than the naked eye could ever dream. But you must be careful with the image. A matter wave is not a physical water wave made of substance sloshing around space. It is not that the electron is stretched out like a little cloudy smear in the simple everyday sense. In quantum physics, the wave describes the structure of the particle's possible behavior. It tells us how likely different outcomes are when the particle interacts with something. Where the wave has certain patterns, the particle is more likely to be found. Where the patterns cancel or vanish, the particle is unlikely to appear. The particle may be detected as one localized event, but before detection, its quantum state can evolve in a wave-like way. This is why matter waves feel so strange. They do not replace particles with ordinary waves. They show that the categories themselves were incomplete. The electron can arrive as a dot, yet its distribution over many trials can carry the signature of a wave. The ripple is not a visible splash. It is the hidden organization of possibility. In atoms, matter waves help explain why electrons occupy stable states instead of simply spiraling into the nucleus. If electrons were merely tiny charged balls moving around a nucleus like planets, classical physics would predict serious problems. But as quantum matter waves, electrons can form standing wave-like patterns around the nucleus. Only certain patterns fit stably. This is one reason atoms have discrete energy levels and why chemistry has order. A standing wave on a guitar string cannot vibrate in just any shape. Only certain patterns fit the string's fixed length. In a somewhat similar spirit, electron matter waves in atoms form allowed patterns. This is not an exact everyday analogy, but it gives the right feeling. Stability comes from wave structure. The atom is not held together by miniature planetary motion, but by quantum patterns that can persist. That single insight reaches into everything around you. The colors of elements, the bonds between atoms, the shapes of molecules, the behavior of solids, the conductivity of metals, the structure of semiconductors, and the chemistry of life all depend on electrons behaving according to matter wave rules. The world does not merely contain matter waves in rare experiments. The world is built from them quietly. Every stable atom in your body depends on this deeper wave logic. The calcium in your bones, the oxygen in your blood, the carbon in your cells, the silicon in your devices, all of it carries the imprint of matter behaving not like little hard beads alone, but like quantum patterns that can fit, combine, exclude, and organize. And perhaps this is the most important lesson. The wave nature of matter is not a decorative weirdness placed on top of reality. It is part of why reality has structure at all. Without matter waves, electrons would not arrange themselves into the shells and patterns that make the periodic table meaningful. Without those patterns, chemistry would lose its architecture. Without chemistry, there would be no cells, no breath, no memory, no voice listening in the dark. The ripples are hidden, but their consequences are everywhere. You do not notice them because your scale is too large, and because the world you experience is the smooth result of countless quantum patterns settling into stable forms. Your hand looks like a hand, not a wave, because its matter wave features are buried under size, temperature, constant interactions, and the enormous complexity of a living body. But underneath, every atom belongs to the same quantum rulebook. Matter waves make particles behave like ripples, and from those ripples come the shapes that feel solid, the bonds that feel permanent, and the materials that build your world. So when you hear the word particle, do not imagine only a tiny dot. Imagine also a wavelength too subtle for your senses, a hidden rhythm connected to motion, a pattern that can bend around atomic structures and reveal itself through interference. Imagine matter not as dead hardness, but as something with a quiet wave nature woven into its movement. The universe becomes softer and more exact at the same time. Softer because the smallest pieces are not as sharply object-like as they seem. Exact because their wave behavior follows rules precise enough to build atoms and power microscopes. In the end, matter waves teach you that the world's firmness is born from something almost musical. Beneath the stillness of a stone, beneath the clarity of a crystal, beneath the living warmth of your own body, particles carry invisible ripples of possibility. They do not behave like ripples because reality is vague. They behave like ripples because, at the smallest scales, rhythm is part of what matter is. The same experiment can give different realities. Imagine setting up the same careful experiment twice, using the same kind of particle, the same clean laboratory, the same patient instruments, and then discovering that nature does not always give you the same kind of reality back, because the answer depends not only on what is there, but on the question your experiment is built to ask. This is one of the most unsettling lessons of quantum physics. The same system can reveal different realities depending on how you choose to measure it. In ordinary life, this sounds wrong. If a box contains a red ball, then whether you shake the box, weigh the box, or shine a light inside it, the ball is still red. The measurement may be clumsy, incomplete, or delayed, but you assume the object already has its properties before you check. Reality, in that familiar picture, is like a room full of furniture waiting in the dark. Turn on one lamp and you see the table. Turn on another and you see the chair. The room does not change just because the lamp changed. But quantum experiments do not fit that comfortable image. At the smallest scales, measuring is not just revealing a pre-written list of properties. It is choosing a physical interaction that makes certain kinds of answers possible, while making other kinds unavailable. The experiment is not a passive window. It is a question shaped in matter, and the form of the question changes the form of the answer. A simple way to understand this is through quantum spin. Though spin is only a name and should not be imagined as a tiny planet rotating. If you prepare a particle and send it through a device that measures spin in one direction, you may get one of two possible results. Prepare the same kind of particle again and measure in that same direction, and you can predict the pattern of results with great accuracy. But now rotate the measuring device and ask about spin in a different direction. The experiment is still about the same kind of particle, still performed carefully, still governed by the same laws, yet nature now gives answers in the language of the new question. Even more strangely, once you measure one direction, you may disturb or reset what can be said about another direction. It is not like discovering that a coin has both a hidden color and a hidden weight. Some quantum properties do not sit together like independent labels waiting to be read. They are incompatible in a deep physical sense. Asking one question clearly can erase the sharpness of another. This is not because scientists are careless, and not because the tools are too rough. It is part of the structure of quantum theory and has been confirmed in many forms. The reality you get is tied to the measurement context. That word context matters. In quantum physics, the same preparation can lead to different observable outcomes depending on the arrangement that follows. If the apparatus is built to test one property, you obtain one kind of fact. If it is built to test a different, incompatible property, you obtain another kind of fact. Both are real results, both can be recorded, both can be predicted statistically, but they are not pieces of one simple picture where every property was already definite in the background. This is where Niels Bohr's idea of complementarity becomes useful. Some aspects of a quantum system are like different faces of reality that cannot be fully displayed at the same time. You can design an experiment that brings out one face or another, but you cannot force the system to behave like a classical object carrying all faces with perfect clarity at once. It is not that one experiment is true and the other is false. It is that quantum reality may not be fully expressible through one single everyday image. It answers according to the whole arrangement. A photon, for example, can be tested in ways that reveal polarization in one direction and then in another direction, and the order and angle of those tests matter. The behavior is not like checking a fixed ID card. It is more like guiding a delicate state through a sequence of interactions, where each interaction helps define what comes next. This is why quantum experiments can feel as if they produce different realities. The word reality here must be used carefully. It does not mean the universe becomes whatever anyone imagines, and it does not mean truth is optional. The rules are strict, the equipment must be real. The results can be repeated in their statistical patterns. Scientists cannot choose any outcome they want, but they can choose which kind of question is physically asked, and that choice determines which kind of answer can become definite. In classical life, you expect measurement to be like reading a number already printed on a page. In quantum physics, measurement is often more like pressing a seal into soft wax. The result is real, but the shape depends on the seal, and once that impression is made, the wax is no longer exactly as it was before. This is also why quantum physics changed the old dream of a completely detached observer. In the classical dream, the universe has all its facts arranged independently, and science simply uncovers them one by one. In the quantum world, science still uncovers truth, but the truth is relational to the experimental setup. The observed fact belongs to the system and the measuring arrangement together. That does not make it subjective in the casual human sense. Your mood does not decide the result. Your belief does not bend the numbers. But the physical design of the measurement does matter. The same preparation, asked different questions, can produce different sets of facts that cannot all be combined into one simple common sense story. This is one reason the quantum world resists being visualized. Your imagination wants a hidden object with hidden properties. Quantum experiments keep replying with contextual outcomes. Your imagination wants the same experiment to reveal the same kind of reality every time. Quantum physics says, first tell me what you mean by same, and first tell me what you are asking. This becomes even more profound in delayed choice and quantum eraser-style experiments, though they must be described carefully. They do not prove that human minds rewrite the past, and they do not allow messages to travel backward in time. What they show is subtler, whether interference-like information or path-like information can be meaningfully assigned depends on the entire experimental arrangement and on what information is physically available. Again, reality is not handing over one naive story that works in all contexts. It is giving a result shaped by the conditions under which the result becomes knowable. The same underlying system can be placed into arrangements that make it appear in different experimental languages. One language speaks of particle-like records, another speaks of wave-like patterns, another speaks of correlations between separated measurements. Each language is valid within its setup, but none should be mistaken for a complete, everyday picture of what the system really was doing in the background. This is not a weakness of quantum physics. It is one of its great strengths because it refuses to lie for comfort. It does not pretend that tiny systems are miniature versions of familiar objects. It tells us exactly what can be predicted, exactly how experiments must be arranged, and exactly where ordinary intuition fails. The lesson is not that reality is unstable nonsense. The lesson is that reality is deeper than a single viewpoint. The same experiment, slightly rearranged, can give a different reality. Because at quantum scales, facts are not always detached, little objects sitting in the dark. Some facts are born through interaction. Some truths require a context to become speakable. And maybe this should make you more humble about all certainty, not only in physics. Even in life, the answer you receive often depends on the question you ask. Look at a person with suspicion, and you may reveal defensiveness. Look with patience, and you may reveal trust. That does not make people unreal. It means relationships are shaped by the conditions under which they unfold. Quantum physics is not psychology, but it carries a similar warning against shallow certainty. Do not assume that one view exhausts the real. At the smallest scales, nature may hold several possible descriptions, each waiting for the right question, each true within its own experimental frame, none reducible to the flat simplicity of common sense. So when you hear that the same experiment can give different realities, do not imagine a universe without laws. Imagine a universe where laws are more precise than your instincts, where measurement is not a mirror but a physical encounter, where facts emerge from the meeting of system and question. The world is not less real because of this. It is more finely structured. It is not a single frozen picture waiting to be seen from every angle at once. It is a reality that reveals different truths under different conditions and asks you to become careful enough, patient enough, and honest enough to know the difference. Quantum rules work, even when they feel absurd. Imagine being handed a rulebook for nature that sounds almost unreasonable at first. A rulebook saying that tiny systems can be described by possibilities instead of fixed stories. That certain measurements cannot be made sharp at the same time. That energy levels come in allowed patterns. That invisible phases matter. And that the deepest predictions often arrive not as guarantees, but as carefully shaped chances. And then discovering that this strange rulebook works more accurately than almost anything human beings have ever created. This is the quiet discipline of quantum physics. It can feel absurd to the imagination, yet it keeps passing the tests. Your mind may resist it because it was trained in a world where things are visible, slow, solid, and separate. You learned reality by dropping objects, opening doors, watching shadows, feeling weight, hearing sounds arrive from somewhere. So when quantum physics says that the microscopic world does not always carry the familiar kind of certainty, your intuition naturally protests. It says, that cannot be how reality works. But science does not survive by feeling comfortable. It survives by prediction, experiment, correction, and repetition. And quantum rules, however strange they feel, keep predicting what nature actually does. This is why physicists trust them. Not because they are easy to picture, not because they satisfy common sense, not because they sound mystical or dramatic. They are trusted because when you use them carefully, they explain the fine structure of atoms, the colors of spectral lines, the behavior of electrons in materials, the stability of chemical bonds, the operation of lasers, the precision of atomic clocks, the tunneling currents in scanning tunneling microscopes, and the tiny magnetic behavior of particles with breathtaking accuracy. A rule can feel absurd and still be true if the world obeys it. In fact, some of the most reliable technologies around you depend on rules that would sound impossible if you met them only as ideas. Consider the transistor, the tiny switching element at the heart of modern electronics. Your phone, computer, camera, car systems, and internet infrastructure all depend on the quantum behavior of electrons inside semiconductors. These devices do not work because electrons behave like little classical balls moving through wires in a simple way. They work because electrons in materials occupy allowed energy bands, because their movement is shaped by quantum structure, because barriers and junctions can be engineered so current flows or stops under controlled conditions. The whole digital world, which feels practical and solid and ordinary in your hand, is resting on rules that once seemed deeply unnatural. Or think about the laser. Its light is not just a stronger flashlight. A laser works because atoms or molecules can be prepared so that many of them release light in a coordinated way, producing a beam that is unusually pure, focused, and orderly. That requires quantum ideas about energy levels and transitions. Yet lasers are now everywhere. In medicine, fiber optic communication, barcode scanners, manufacturing, eye surgery, scientific measurement, and the quiet red dot of a presentation pointer. What once sounded like an abstract disturbance in the human picture of reality became a tool sharp enough to cut metal and gentle enough to repair vision. This is one of the great lessons of quantum physics. Usefulness does not wait for intuition to approve. Nature does not ask whether the rules feel reasonable before allowing engineers to build with them. And the accuracy goes even deeper than technology. Quantum electrodynamics, the theory describing how light and charged particles interact, has produced some of the most precise agreements between theory and experiment ever achieved. One famous example involves the electron's magnetic moment, a tiny property that can be measured and predicted to extraordinary precision. The agreement is so fine that it is not merely a success. It is a kind of intellectual thunderclap, a reminder that the strange mathematics is not floating away from reality, but touching it almost exactly. This matters because it separates quantum physics from empty speculation. A beautiful idea can be wrong. A strange idea can be right. The difference is whether nature answers back. Quantum physics has been questioned, challenged, tested, and refined for more than a century. And while debates about interpretation remain open, the working rules continue to deliver. That is an important distinction. Physicists may argue about what the quantum state truly means, what measurement really is, or whether reality is best understood through one interpretation or another. But the practical rules for calculating outcomes have proven themselves again and again. In other words, we may still argue about the story behind the machinery, but the machinery works. This is why quantum physics can be both philosophically unsettling and scientifically dependable. It does not give the mind a simple picture, yet it gives the laboratory reliable numbers. It feels absurd because your imagination wants a movie, a clear scene with tiny actors moving through tiny spaces. Quantum theory often gives something closer to a recipe for what can be observed, how likely it is, and how systems transform when they interact. That can feel unsatisfying if you demand an everyday image. But perhaps the demand itself is the problem. Why should the foundation of reality look like the furniture of human experience? Why should atoms behave like pebbles simply because pebbles are what your hands understand? The history of science is full of moments when the universe forced human intuition to grow. It once felt obvious that Earth was still and the heavens moved around it. It once felt obvious that heavy things should fall faster than lighter things. It once felt obvious that time should pass the same way for everyone. Each time, nature turned out to be larger than the instincts built from ordinary life. Quantum physics is another such expansion, perhaps the deepest one, because it does not just revise one belief. It revises the style of belief itself. It teaches you to trust evidence over comfort, pattern over mental pictures, precision over familiarity. And there is a calm beauty in that. The absurd feeling does not mean the universe is irrational. It means your old sense of rationality was too small. Quantum rules are not a collapse into nonsense. They are a higher discipline hidden beneath the appearance of nonsense. They are strict, testable, and mathematically coherent, but their coherence is not the kind your childhood senses expected. They work in the quiet places where intuition has no authority. They work inside atoms, inside chips, inside clocks, inside stars, inside the chemistry that makes your body possible. They work when no one is emotionally ready for them. They work whether or not the mind can turn them into a comfortable picture. So when quantum physics feels absurd, the better response is not to reject it too quickly or romanticize it too loosely. The better response is to ask what kind of truth can feel absurd and still build the modern world. Maybe the deepest reality does not need to resemble the surface reality that trained you. Maybe understanding is not always the same as picturing. Maybe some truths first arrive as discomfort, then become calculation, then become technology, then become ordinary life. And in the end, that may be the most humbling lesson of all. The universe is not required to be intuitive to be lawful. It can be strange and exact, bewildering and reliable, almost impossible to imagine, and still power the devices in your hand, the medicine in your hospitals, and the instruments that measure time with astonishing care. Quantum rules work even when they feel absurd, because nature is not built to flatter human instinct. It is built according to its own deeper order, and science is the slow, patient art of learning to listen when that order speaks in a language we did not expect. Wave functions describe possibility, not just location. Imagine being given a map that does not show where a traveler is standing, but instead shows every place the traveler could meaningfully be found, every kind of question you might ask about the journey, and the hidden relationships between answers that have not happened yet. That is closer to what a wave function does in quantum physics. It is often introduced as if it were only a fuzzy cloud around a particle, a way of saying, the particle might be here, or it might be there. But that picture is too small. A wave function is not just a blurry location marker. It is a deeper description of possibility itself. It tells physics how a quantum system is prepared, how its possible outcomes are arranged, how those possibilities change over time, and what patterns can appear when the system finally interacts with something measurable. If you imagine a particle as a tiny object hiding somewhere inside a fog, you miss the most important part. The wave function is not simply a fog of ignorance. It is a structured description, carrying information about what nature can reveal if you ask different questions. Location is only one kind of question. You may ask where a particle is found, but you may also ask about its motion-related behavior, its energy, its spin, its polarization, or how it is related to another system. The wave function is the quiet source from which those possible answers are drawn. It is like a musical score before sound enters the room. The score is not the performance, but it contains the structure that makes certain performances possible and others impossible. In the same way, the wave function is not the dot on the detector, not the final click, not the visible result, but it carries the organization behind those results. For a single particle, the wave function can tell you how possibility is distributed across space. In some regions, the particle is more likely to be detected. In others, less likely. But even there, it is not just a pile of chances. It contains a kind of inner structure that determines how the system evolves, how it spreads, how it responds to barriers, fields, and boundaries. This is why a particle trapped inside a tiny region, like an electron in an atom or a particle in a small box, cannot simply have any pattern it wants. The wave function must fit the physical situation. It must satisfy the rules imposed by the environment, the forces involved, and the boundaries around it. From this fitting come the allowed states of atoms, the shapes of orbitals, and the predictable behavior behind chemistry. When chemists show atomic orbitals as lobes and shapes, they are not showing little paths traced by electrons. They are showing patterns derived from wave functions, regions where an electron is more likely to be found if measured. Those shapes matter. They help explain how atoms bond, why molecules have certain geometries, why carbon can build complex structures, why materials conduct or insulate. why the microscopic architecture of matter gives rise to the visible world. But a wave function becomes even stranger when more than one particle is involved. Your everyday imagination wants each particle to have its own private possibility cloud in ordinary space, like separate weather systems drifting around. Quantum physics does not always allow that simple separation. For multiple particles, the wave function can describe the whole system at once, not as a set of independent maps, but as one combined structure. In technical terms, it often lives in a space of configurations, meaning it describes possible arrangements of all the particles together. This matters because the possibilities may be linked. The answer for one part of the system may not be fully independent of the answer for another. The wave function can contain relationships, not just individual locations. It can say, in effect, if this is found one way, that is more likely to be found another way. This is one reason quantum theory is so hard to reduce to a simple picture. The wave function is not always a picture in physical space. Sometimes it is a description of possible worlds of arrangement, a deep bookkeeping of how parts of a system belong together before measurement gives a definite record. And yet it is not merely a human guess. It evolves according to strict rules. Left undisturbed, a wave function changes smoothly and predictably, like a carefully guided unfolding of possibility. But when a measurement occurs, the description must be updated to match the result that actually happened. This update is one of the great interpretive mysteries of quantum physics. Some physicists speak of collapse. Others describe measurement in terms of interaction with the environment. Different interpretations argue about what the wave function really is: a physical reality, a tool for predicting experience, a state of knowledge, or part of a larger structure. But regardless of interpretation, the wave function works. It allows scientists to calculate the probabilities of experimental outcomes with extraordinary precision. It is the central object in non-relativistic quantum mechanics. And even where more advanced theories are needed, the same basic lesson remains. Reality at small scales is described by structured possibility before it is described by definite appearance. This is why the wave function should not be reduced to where the particle is. Location is only the most visual answer, the one easiest for the human mind to crave. But quantum physics is not built for the comfort of visualization. The wave function can describe a system that has a definite energy but no sharply defined location in the everyday sense. It can describe a particle prepared so that its motion is more sharply known while its position is spread out. It can describe states that are stable, states that change, states that combine, states that are delicate enough to be destroyed by interaction. It is more like a full grammar of possible answers than a simple address. And perhaps this is why the idea feels so quietly unsettling. Your mind wants reality to exist first as a set of fixed facts, with possibility merely reflecting what you do not yet know. The wave function suggests something deeper. Possibility can have form before fact appears. Not vague possibility, not empty maybe, but ordered possibility, shaped by laws, prepared by conditions, and capable of producing exact patterns over repeated trials. This does not mean the universe is imaginary. It means the visible world may be the surface expression of a more subtle structure beneath visibility. A wave function is real enough to guide the behavior of atoms, real enough to explain spectra, bonds, tunneling, stability, and quantum technologies, even if no one can hold it like an object. It is a reminder that the foundations of reality may be written not in the language of things already decided, but in the language of what can become true under the right question. So when you hear wave function, do not picture only a mist around a particle. Picture a living catalogue of potential outcomes, a hidden architecture of relationships, a silent score that tells matter how it may answer when the world asks. It describes possibility, not just location, because quantum reality is not merely about where something is. It is about what can happen, how strongly it can happen, how different possible answers are connected, and how the definite world slowly rises from a deeper field of structured maybes. Measurement turns potential into one result. Imagine a quiet room full of possible music. every note waiting in silence, every melody suspended before the first finger touches the key, and then one key is pressed. One sound enters the air, and the room is no longer a field of everything that might be heard, but one actual vibration moving through time. That is the simplest way to feel what measurement does in quantum physics. It turns potential into one result. Before measurement, a quantum system is often described not as a finished fact, but as a structured set of possible outcomes. This does not mean it is imaginary, and it does not mean it is waiting for a human mind to give it permission to exist. It means that, at the smallest scales, nature can preserve more than one possible answer in its description until a physical interaction forces one answer to become recorded. Measurement is not just looking in the ordinary sense. It is not a pair of eyes doing something mystical. It is an encounter strong enough to create a fact. A detector clicks. A screen darkens at one point. An atom absorbs energy. A tiny electrical signal appears. A device stores information that can later be read. Once that happens, the open potential has become one actual event. A quantum system that could have produced several possible results has now produced this result, here, now, in this apparatus. The difficulty is that your everyday mind wants every result to have been waiting there all along, like a coin hidden under a cup. You lift the cup and discover heads, so you assume heads was already the truth before you checked. But quantum measurement does not always fit that simple discovery story. In many experiments, the best description before measurement is not "the answer is hidden but unknown." It is "the system is arranged so that several outcomes are physically possible, with precise probabilities, and the measurement will bring one of them into the record." This is why measurement feels so central and so strange. It is the doorway between the delicate quantum description and the definite world of experience. Before the doorway, physics speaks in possibilities. After the doorway, the laboratory notebook contains a number, a spot, a click, a yes, a no. The potential has narrowed into one result. A useful example is an atom that can emit light. Before emission, the atom may be in an excited state, carrying extra energy. Quantum theory can tell us the probability that it will release that energy within a certain time, but it does not give the same kind of exact personal schedule that you would expect from a clockwork machine. When the atom finally emits a photon, the event becomes definite. Energy has been released. A detector may later absorb that photon and register a signal. The measurement record is no longer a cloud of possible times or possible outcomes. It is one occurrence. Something happened. The same kind of transition appears in modern quantum devices. A superconducting qubit, for example, can be prepared in a delicate combination of two possible readout results. While protected from disturbance, that state can be manipulated as a genuine quantum resource. But when the qubit is measured, the device does not show the whole delicate combination directly. It returns one result from the allowed set. The art of quantum technology is partly the art of controlling potential before measurement, and then reading one outcome reliably afterward. This is not a failure of the system. It is the system behaving quantum mechanically. What existed before measurement was not a visible menu with all options glowing on a screen, but a physical state whose possible results were arranged with exact structure. Measurement converts that structure into a single recorded answer. The mystery deepens because measurement usually changes the system. If you measure a fragile quantum state, you are not merely copying information out of it like scanning a page. You are interacting with it. That interaction can destroy the previous state, prepare a new one, or entangle the system with the measuring device and environment. In ordinary life, measuring often seems passive. A ruler does not greatly change the length of a table. A thermometer may slightly affect the water it touches, but not enough to matter in simple cases. In quantum physics, the interaction cannot always be ignored. To know something, the system must leave a trace somewhere else, and leaving a trace means becoming linked to something larger, warmer, messier, and more difficult to keep in a delicate quantum condition. This is why the world around you looks definite. The environment is constantly measuring in a broad physical sense. Air molecules, photons, heat, surfaces, and surrounding matter interact with objects all the time, continually creating records and destroying delicate alternatives. You do not see chairs in ghostly combinations because they are never isolated from the world long enough for such quantum potential to remain visible at your scale. The environment helps turn potential into stable facts long before your conscious awareness enters the scene. This is called decoherence, and while it does not solve every philosophical question about measurement, it explains why quantum weirdness becomes hidden in everyday life. It shows how fragile alternatives lose their ability to interfere when information leaks into the surroundings. The result is the familiar world. One pointer position, one mark on a screen, one outcome that can be shared and remembered. Still, measurement remains one of the deepest puzzles because the theory describes smooth evolution before measurement, then definite results after measurement, and the exact meaning of that transition is still debated. Different interpretations tell different stories. Some say the wave function collapses. Some say all outcomes continue in separate branches, while observers experience only one. Some say the quantum state is mainly information, updated when a result is known. Others search for deeper physical mechanisms. But the experimental fact remains. When we measure, we get one result. Not a smear of all visible answers. Not a half result. One result. The screen shows a point. The counter clicks once. The readout gives a value. The definite world appears one event at a time, and perhaps that is the part that should stay with you. Measurement is not merely the act of finding reality. In quantum physics, it is part of how reality becomes definite in practice. Potential is not useless or unreal before measurement. It guides what can happen. It shapes the odds. It carries the structure of the system. But potential is not the same as a recorded fact. A fact is what survives interaction. A fact is what can be copied into the world, written into a detector, remembered by a device, compared by observers, placed into history. Before measurement, nature holds a disciplined openness. After measurement, the openness has narrowed into one trace. This is not magic, and it is not a license to say that anything is possible. The possible results are constrained. The probabilities are precise. The measuring setup matters. The laws remain strict. But within those laws, quantum physics shows a universe where the path from possibility to actuality is not as simple as common sense expects. So when you think about measurement, do not imagine only a scientist staring at an instrument. Imagine a bridge. On one side, there is a quiet structure of potential outcomes, real enough to guide the future, but not yet reduced to a single public fact. On the other side, there is the world you know. Marks, signals, records, memories, results. Measurement is the crossing. It is the moment when the many things nature could have said become the one thing nature did say. And in that crossing, the universe becomes readable, one fragile answer at a time. Tiny systems can stay undecided until interaction. What if the smallest pieces of nature are not rushing to become definite, not eager to pick one answer, not forced to settle into the kind of reality your senses expect, but can remain quietly suspended in an undecided condition until something finally interacts with them? This is one of the most delicate truths in quantum physics. Tiny systems can preserve openness in a way large objects almost never do. In daily life, indecision belongs to minds. A person can hesitate between two doors, two words, two futures. But a physical object seems different. A lamp is either on or off. A glass is either broken or whole. A key is either in your pocket or not. The ordinary world does not seem to tolerate unresolved physical states. It gives you outcomes quickly, almost aggressively. But tiny quantum systems, when they are carefully isolated from their surroundings, can remain in what physicists call a superposition, not a messy confusion, not a hidden ordinary answer waiting underneath, but a genuine quantum condition in which more than one possible result remains part of the system's description. The crucial phrase is, until interaction. A quantum system does not need a human being to stare at it. It does not wait for consciousness like a shy actor waiting for an audience. What matters is physical contact with something that can carry away information. A detector, a photon, a nearby atom, a surface, heat, vibration, even the surrounding environment. Interaction is the great divider between delicate possibility and stable record. Before interaction, a tiny system can keep several alternatives alive in a coherent relationship. After interaction, those alternatives can become separated, disturbed, or turned into one usable fact. This is why quantum laboratories work so hard to protect tiny systems from the world. Scientists trap ions in electromagnetic fields, cool atoms until their motion slows almost to stillness, isolate superconducting circuits inside extremely cold refrigerators, and shield delicate states from stray noise. They are not doing this for drama. They are doing it because the quantum undecidedness is fragile. The surrounding world is constantly trying to interrupt. Air molecules collide, thermal energy shakes, light scatters, materials vibrate. Every unwanted touch can leak information and push the system toward a more definite condition. In that sense, the classical world is not classical because it is fundamentally different matter. It is classical because it is constantly interacting. A dust grain floating in sunlight is being struck by photons and air molecules at every moment. Its position is recorded by the environment again and again. It cannot keep its quantum alternatives cleanly related for long. But an electron, an atom, or a carefully engineered quantum bit can sometimes be protected well enough to remain undecided in the quantum sense. That undecidedness is not laziness. It is a resource. Atomic clocks use carefully controlled quantum states to measure time with extraordinary precision. Quantum computers try to use protected superpositions to process information in ways ordinary bits cannot. Interferometers use delicate quantum coherence to measure tiny changes in distance, fields, or motion. In all these cases, the power comes from letting a tiny system remain open long enough for its possible alternatives to evolve together. Only later is the system read out through interaction. This should change the way you imagine not decided. In ordinary speech, undecided means vague, weak, or unfinished. In quantum physics, undecided can be structured, exact, and useful. The system is not blank. It carries a carefully prepared relationship between alternatives. A trapped ion, for example, can be placed into a controlled combination of two internal energy states. That does not mean the ion is confused like a person unable to choose. It means the quantum state has been arranged so both possible measurement outcomes are present in a precise physical way. Scientists can even manipulate that state, rotate it, let it evolve, and cause its alternatives to reinforce or cancel when later tested. If the state were merely ordinary ignorance, this would not work. You cannot use ignorance as an engine. Quantum superposition has operational consequences. It can be verified by how the system behaves, how it responds to pulses, how it produces interference, how it changes when exposed to controlled interactions. Yet this openness survives only as long as the system remains sufficiently isolated from information-leaking contact. Once the environment gains a record, even a tiny one, the undecided character becomes hidden or effectively lost. This is the process that helps explain why you never see a cat both alive and dead in normal life. Despite the famous thought experiment, the cat is a large, warm, complex organism in constant interaction with air, light, cells, heat, and countless internal processes. Any delicate quantum superposition involving such a large system would be destroyed unimaginably quickly in practice. The point of the thought experiment was not that cats actually wander around half real in living rooms. It was meant to reveal the tension between quantum rules and the definite world we experience. Tiny systems can stay undecided because they can sometimes be isolated. Large systems almost never can. The difference is not magic. It is contact. The world is always touching itself, and every touch is a kind of conversation that makes some possibilities harder to keep together. This gives interaction a deeper meaning than simple collision. An interaction can be a transfer of energy, a scattering of light, a coupling between fields, a disturbance that creates a trace somewhere else. The trace does not have to be seen by a person. If information has escaped into the environment in a way that could distinguish the alternatives, the fragile quantum relationship changes. the system becomes less like a quiet chord held in the dark and more like a note that has already been recorded. And once the record spreads into the environment, it is extremely difficult to undo. That is why quantum coherence feels so precious. It is not merely smallness that matters. A tiny system in a noisy environment can lose coherence quickly. A larger engineered system, if carefully protected, may show quantum behavior under the right conditions. The boundary is not simply size. It is isolation, control, and the flow of information. This is one of the most educational parts of the topic because it corrects a common misunderstanding. Quantum physics is not a separate universe that exists only below a certain size, while ordinary physics begins above it with a hard border. The difference is gradual and practical. Quantum rules are always there, but their delicate features are often washed out by interaction. The more a system becomes entangled with its surroundings, the more its alternatives stop behaving like a single coherent possibility structure and start behaving like ordinary outcomes. The world you experience is therefore not proof that quantum undecidedness is unreal. It is proof that you live in an environment overflowing with interactions. Your room is constantly being measured by light. Your body is constantly exchanging heat. Your thoughts depend on warm, wet, noisy biological systems, where fragile quantum alternatives usually do not survive as meaningful superpositions at the scale of experience. Reality feels definite because the universe is never quiet around you, but deep inside controlled experiments, where the noise is reduced and interactions are delayed, nature reveals that definiteness is not always immediate. A tiny system can wait. It can hold open more than one answer. It can remain poised between outcomes, not forever, not freely, not outside law, but until the next interaction forces its possibilities to become part of a larger record. And maybe this is the softest wonder hidden in the quantum world. Reality is not always born fully hardened. Sometimes it is held gently, conditionally in a state of disciplined openness. The smallest systems can stay undecided not because they lack reality, but because their reality has not yet been asked to settle into one public fact. They are like breath before speech, like a note before it is played, like dawn before the first edge of the sun crosses the horizon. Interaction is the moment the silence breaks. It is when the quiet potential of the tiny world becomes an answer the larger world can remember. Quantum states can be fragile like soap bubbles. Imagine blowing a soap bubble into cold morning air and watching it float with perfect colors for a few seconds, its surface holding a delicate pattern of light, tension, and breath until the smallest touch, the faintest dust grain, or a shift in wind makes the whole fragile structure collapse into nothing you can hold. A quantum state can be fragile in a similar way, not because it is unreal, and not because it is weak in a meaningless sense, but because the special order that makes it quantum can be easily disturbed by the surrounding world. This is one of the most important truths behind modern quantum science. The strange features we talk about are not usually loud, durable, and easy to preserve. They are delicate arrangements, often requiring isolation, cold temperatures, careful timing, and extraordinary protection. A quantum state is not just a particle sitting somewhere. It can include a precise relationship between possibilities, a controlled balance between outcomes, or a subtle alignment that allows interference, superposition, or entanglement to exist. But that balance can be ruined when the system becomes entangled with its environment in an uncontrolled way. When heat shakes it, when stray light touches it, when electrical noise leaks in, when nearby atoms vibrate, or when the measuring equipment itself is not quiet enough. The state may not disappear in the simple sense that the particle is destroyed. Instead, the special quantum information inside the state becomes scrambled, spread into the environment, and no longer usable. This is why scientists sometimes speak of quantum coherence as something that must be preserved. Coherence is like the shared timing inside a choir. If every voice holds the right relationship to every other voice, a clear harmony emerges. But if random noise enters, if each singer drifts out of rhythm, the harmony dissolves even though the singers are still there. In the same way, a quantum system can still physically exist after disturbance, but the delicate relationship that made its state useful may be lost. This is a crucial distinction. Fragility does not mean quantum states are imaginary. A soap bubble is real, even if it bursts easily. A snowflake is real, even if warmth destroys its pattern. A whispered note is real, even if traffic noise hides it. Quantum states are real enough to be prepared, controlled, measured, and used in technology. But the more distinctly quantum they are, the more carefully they often need to be protected. This is why many quantum experiments look almost extreme from the outside. Atoms may be trapped in vacuum chambers where nearly all air has been removed. Lasers may cool particles until they barely move compared with ordinary thermal motion. Superconducting quantum circuits may be placed inside refrigerators colder than outer space. Not for drama, but because warmth is noise, and noise is the enemy of delicate phase relationships. Ion traps use electric fields to hold charged atoms nearly motionless in space. Quantum dots confine electrons in tiny regions of material. Photons are guided through carefully designed optical paths, so their polarization or timing remains controlled. Each approach is different, but the goal is similar: protect the state long enough to do something meaningful before the outside world blurs it. This fragility is one of the biggest challenges in building quantum computers. A normal computer bit is rugged by comparison. It can be copied, refreshed, stored, and checked without much trouble. A quantum bit is different. It can hold a delicate state that gives quantum computing its power. But measuring it too directly can destroy the very information you wanted to use, and environmental disturbance can corrupt it before the calculation is finished. This is why quantum error correction is so important. Scientists cannot simply clone an unknown quantum state and keep backup copies, because quantum information does not allow that in the ordinary way. Instead, they spread information across groups of physical quantum bits so that certain errors can be detected and corrected without reading the fragile state directly. It is like protecting a soap bubble by not trying to freeze the bubble itself, but by creating a careful chamber around it, sensing the wind without touching the film, and adjusting the air before the bubble tears. The engineering is incredibly difficult, and this is one reason useful large-scale quantum computers are so hard to build. The theory promises power, but the states that carry that power are easily damaged. Yet this fragility is also part of what makes quantum systems valuable. Because they are so sensitive, they can become extraordinary sensors. A state that is easily disturbed by magnetic fields, gravity, motion, or time can be used to measure those things with remarkable precision if the disturbance is controlled rather than random. Atomic clocks depend on quantum states that respond in extremely reliable ways, allowing time to be measured with astonishing accuracy. Quantum sensors can detect tiny magnetic fields, small accelerations, and subtle changes that ordinary devices might miss. So the same delicacy that makes quantum states hard to protect also makes them powerful tools. A soap bubble is fragile, but its surface reveals the slightest breath of air. A quantum state is fragile, but that fragility can become sensitivity. This should change how you think about weakness. In the quantum world, fragility is not failure. It is the price of subtle structure. The more refined the pattern, the easier it is for noise to destroy it, but also the more information that pattern can carry when preserved. A diamond is strong because its atoms are locked into a rigid structure. A quantum state can be powerful for the opposite reason, because it is open to delicate relationships that ordinary objects cannot maintain. Its strength is not hardness. Its strength is precision, and precision needs quiet. The ordinary world is not quiet. It is warm, bright, crowded, vibrating, colliding, exchanging information at every moment. This is why the quantum strangeness beneath reality is usually hidden from your senses. Not because it is absent, but because the world is constantly smearing the fragile patterns before they can become visible at your scale. You live inside a storm of interactions, yet your experience feels stable because the fragile quantum details have already been washed into ordinary facts. In the laboratory, scientists do the opposite. They carve out silence. They remove heat, shield against vibration, filter signals, reduce stray fields, and slow the world down around a tiny system so that its quantum state can survive a little longer. Sometimes that lifetime is still incredibly short. Sometimes it lasts long enough to perform a calculation, send a secure signal, or test a deep idea about nature. Every extra fraction of survival matters. Every improvement in isolation becomes a step toward controlling the invisible, and there is a quiet beauty in this effort. Human beings, made of warm and noisy matter, are trying to create pockets of stillness where nature's most delicate patterns can remain unbroken. We are trying to listen to the universe at the volume of a whisper. So when you hear that quantum states can be fragile like soap bubbles, do not imagine them as unreal things that vanish because they were never there. Imagine them as precise structures that need the right conditions to keep their shape. Imagine a thin film of possibility reflecting hidden colors, beautiful because it is ordered, vulnerable because it is open. The quantum world is not only strange because it defies intuition. It is strange because its deepest powers often arrive in forms that cannot survive carelessness. To work with them, you need patience, protection, and respect. And maybe that is the soft lesson at the center of it. Not everything powerful is loud, solid, or permanent. Some of the most important structures in nature are brief, quiet, and easily broken. They must be held gently to be understood. The classical world is an emergent illusion. Imagine standing so close to a painting that all you see are rough islands of pigment, tiny cracks, uneven strokes, and accidental-looking fragments of color, then slowly stepping backward until the chaos becomes a face, a landscape, a sky, a world that feels whole, smooth, and obvious. That is one way to understand why the classical world may be an emergent illusion. It is not an illusion in the cheap sense, not fake like a trick mirror or a dream that vanishes when you wake up. The table really holds your cup. The moon really follows its orbit. A falling glass really breaks. Your body really moves through rooms, touches surfaces, hears sound, and remembers yesterday. But classical reality, the familiar world of definite objects, clear paths, stable positions, and predictable motion, may not be the deepest layer of what exists. It may be what quantum reality looks like after you step far enough back, after countless microscopic details blend together, after delicate possibilities are washed into stable patterns, after the universe becomes large enough, noisy enough, and averaged enough to seem simple. In classical physics, the world feels like a collection of things with fixed properties. A ball has a position, a car has a speed, a planet has an orbit, a clock ticks forward. Causes produce effects in a way that can be pictured, tracked, and often predicted. This picture is so successful at human scales that it is easy to mistake it for the foundation of reality itself. It built bridges, engines, aircraft, machines, calendars, and the first great understanding of the heavens. But quantum physics suggests that this solid-looking layer is more like a pattern that emerges from something beneath it, the way temperature emerges from the motion of countless molecules. Temperature feels like a direct property. You place your hand near a fire and feel warmth. Yet warmth is not a tiny substance hidden inside the flame. It is the large-scale result of many microscopic motions. No single molecule has temperature the way a cup of tea does. Temperature appears when many particles act together and their individual details are summarized into one usable quantity. In a similar way, classical reality may appear when many quantum systems interact so densely that their stranger features become practically invisible. A single atom can behave in ways that challenge common sense, but a baseball contains an enormous number of atoms, all interacting with one another and with the surrounding air, light, ground, and heat. The fragile quantum alternatives that might be meaningful in an isolated laboratory system do not remain clean and visible in a baseball flying across a field. They become entangled with the environment, dispersed into countless degrees of freedom, and impossible to recover in any practical sense. What remains is a stable, trackable object following a path that classical physics can describe extremely well. This is why the classical world is not simply wrong. It is a powerful approximation. It is what the deeper rules look like when the system becomes large, warm, and constantly connected to everything around it. The illusion is not that the world exists. The illusion is that the world is fundamentally as simple as it appears. Think of a wave on the ocean. From far away, it looks like one object moving toward the shore. You can point to it and say, "There is the wave." But the wave is not a separate thing made of special wave material. It is a coordinated behavior of water molecules, wind, gravity, and energy passing through a medium. The wave is real, but it is emergent. It exists as a pattern, not as an independent substance. The classical world may be similar. A chair is real, but its chairness is not found in one atom. A path is real, but its smoothness may come from the collective behavior of many quantum events. A solid object is real, but its definiteness may be a large-scale appearance produced by interactions that constantly stabilize one outcome over countless others. This is why emergence is such an important idea. Emergence means that a higher-level pattern can be real and useful, even though it is not fundamental in the same way as the microscopic rules beneath it. A flock of birds has a shape, but no single bird contains the flock. A city has traffic, economy, mood, rhythm, but no single street contains the city's whole behavior. A mind has thoughts, but one neuron alone does not hold a complete idea. In the same way, the classical world may be the emergent pattern of quantum matter behaving collectively. You do not need to follow every atom in a raindrop to understand that it falls. You do not need to calculate every molecule in a storm to know wind can bend trees. At larger scales, new descriptions become not only convenient but necessary. They are the level at which reality becomes usable to beings like us. And perhaps that is where the word illusion must be handled gently. An illusion is often assumed to mean false, but some illusions are better understood as compressed truths. The smooth color on a screen is an illusion created from pixels, but the image is still meaningful. The motion in a film is an illusion created from still frames, but the story can still move you. The solidity of everyday objects is an emergent experience created from forces, fields, and quantum restrictions, but the object can still stop your hand. The classical world is like this: a stable interface, a simplified layer, a reality your senses can survive inside. It hides the microscopic complexity, not because it wants to deceive you, but because too much truth at once would be unusable. If you could directly experience every quantum detail in the room, you would not see a room. You would drown in information. Your nervous system gives you chairs, walls, faces, distances, and motion, because those are the patterns that matter for living. Science then comes along and says, those patterns are real, but they are not the final depth. The deeper world does not look like the surface. This is why classical physics and quantum physics are not enemies. Classical physics is what quantum physics becomes when the conditions allow the strange details to average into ordinary behavior. The older theory still works beautifully where it is meant to work. It fails only when you ask it to explain the foundation beneath its own success. That is not a weakness. It is how knowledge grows. Each layer of science reveals where the previous layer was powerful and where it was incomplete. Newton's laws did not stop being useful when relativity and quantum theory arrived. They became part of a larger map. They described the calm roads, not the hidden engine of all roads. And the classical world, with all its firm objects and clean motions, may be the calm road your mind walks every day, while quantum physics describes the deeper terrain from which that road arises. There is a strange comfort in this if you let it settle slowly. The world you trust is not destroyed by learning it is emergent. A rainbow is emergent, but it is not meaningless. Life is emergent, but it is not fake. Conscious experience itself may arise from countless physical processes, yet your pain, wonder, love, and memory are not made worthless by that. Emergence does not remove reality. It gives reality layers. It says that something can be dependent and still genuine, not fundamental and still precious. The classical world may be an emergent illusion, but it is the illusion that lets stars become skies, atoms become bodies, vibrations become music, and quantum events become the stable stage on which your life unfolds. So when you place your hand on a table, watch a shadow move across the floor, or see rain sliding down a window, you are not living in a lie. You are living in a higher level truth, a softened translation of a deeper language. Beneath the calm surface, the quantum world does not vanish. It is simply hidden by scale, interaction, and complexity. The miracle is that out of such strangeness, such delicacy, such microscopic uncertainty, a world as dependable as this can rise at all. The classical world is an emergent illusion, not because it is unreal, but because it is reality, viewed from the distance where the fragments finally become a picture. Decoherence hides quantum weirdness from daily life. What if the reason your coffee cup never appears in two places at once is not that the quantum world has disappeared, but that the room around it is constantly stealing its secrets before you ever get a chance to notice them? This is the quiet role of decoherence, one of the most important ideas for understanding why daily life looks normal, even though the microscopic rules beneath it are so strange. Decoherence is not a new force, not a magical switch, and not a final solution to every mystery of measurement. It is the process by which fragile quantum relationships become hidden when a system interacts with its environment. In simple terms, quantum weirdness survives best when a system is isolated, protected, and kept from leaking information. But the everyday world is the opposite of isolated. It is crowded with light, heat, air molecules, vibrations, dust, sound, radiation, and countless tiny contacts. Every object around you is constantly interacting with everything else. Photons bounce off your desk, air molecules strike your skin, heat flows from warm things to cooler things. The floor trembles faintly from distant motion. Even in a quiet room, the physical world is not silent. It is always exchanging information. And that exchange is what hides the delicate quantum behavior that might otherwise seem impossible to ignore. To understand this, imagine a tiny quantum system holding several possible alternatives in a careful relationship, almost like a secret written in ink that only remains readable if the paper is kept perfectly dry. The environment is like humidity spreading through the room. It does not need to tear the paper apart. It only needs to blur the ink enough that the original message can no longer be read. In quantum physics, a system may start with possibilities that can still interfere with one another, meaning the alternatives are not yet behaving like separate ordinary facts. But when the system interacts with the environment, information about those alternatives can spread outward. A photon may scatter differently depending on where a particle is. An air molecule may bounce in a way that carries a tiny clue. A detector may become slightly correlated with one possible outcome rather than another. Each interaction leaves a trace, and once enough traces escape into the surroundings, the original alternatives can no longer act as one coherent quantum whole. The weirdness has not necessarily been destroyed in the sense of being erased from the universe. More carefully, it has become dispersed into relationships with the environment, spread so widely and messily that no ordinary observer can bring it back together. This is decoherence, the fading of visible quantum coherence because the system has become entangled with the world around it. The important point is that decoherence does not require a person to look. The universe does not wait for human eyes. A grain of dust floating in sunlight is being monitored by the environment constantly because photons from the sun scatter off it in all directions. Those scattered photons carry information about the dust grain's position into the room, into the air, into space. In an incredibly short time, the dust grain's delicate quantum alternatives become effectively separated from one another. That is why the dust grain appears to have one definite position. Not because quantum theory stops applying to it, but because the environment has made any interference between different positions practically inaccessible. The world becomes classical looking because it is overflowing with accidental witnesses. Every surface is watched by light. Every warm object broadcasts infrared radiation. Every object in air is struck again and again by molecules. The environment is not conscious, but it records. It records badly, messily, and uncontrollably. But it records enough to hide the fragile relationships that make quantum effects visible. This is why quantum experiments often demand extreme isolation. If scientists want an atom, ion, photon, or superconducting circuit to keep its quantum behavior, they must prevent the environment from learning too much about it too soon. They remove air, lower temperature, shield against electromagnetic noise, reduce vibration, and carefully control every interaction. They are not trying to make the system strange. They are trying to stop ordinary reality from rushing in too early. Decoherence explains why the border between quantum and classical is not a sharp wall. It is not that electrons obey quantum rules and cats obey completely different rules. Instead, large warm objects are so deeply connected to their environments that their quantum coherence disappears from practical view almost instantly. A molecule in a vacuum can sometimes show interference. Larger molecules have even been used in experiments showing wave-like behavior under very controlled conditions. But as systems become bigger, warmer, and more exposed, protecting coherence becomes much harder. The environment gathers information too quickly. The quantum possibilities stop behaving like a unified pattern and start behaving like separate alternatives, the kind your everyday mind understands. This is why decoherence is often described as the bridge between the quantum world and the classical world. It shows how familiar definiteness can emerge without needing to claim that quantum rules simply fail. The rules remain underneath, but their strangest visible effects are hidden by interaction. There is a subtle difference here that matters. Decoherence explains why interference between alternatives disappears and why certain stable outcomes become favored in practice. It helps explain why we see a world of definite records instead of obvious superpositions. But by itself, decoherence does not fully explain why one specific outcome is experienced rather than another. That deeper question belongs to the interpretation of quantum mechanics and remains debated. Some interpretations say the wave function collapses. Others say all branches continue but observers find themselves in one branch. Others take different approaches. Decoherence does not end that debate, but it changes it profoundly. It shows that once a system becomes entangled with its environment, the alternatives stop interacting with one another in any practical way. They become like stories written on pages that have been scattered across the universe, impossible to recombine. From inside one story, the others no longer matter for daily experience. This is why decoherence feels less dramatic than science fiction, but more powerful than magic. It is not a cosmic judge choosing reality. It is the slow, constant leaking of information into the world. It is why your chair stays chair-like, why your keys remain in one place, why a ball follows a visible path, why your reflection does not blur into 1,000 possible faces. The ordinary world is stable because it is noisy. That sounds almost backwards. We usually think noise creates confusion. But in the transition from quantum to classical, environmental noise helps create the appearance of definiteness by destroying delicate coherence. The same noise that prevents quantum weirdness from being visible also gives daily life its firmness. Without decoherence, the world might not settle into the reliable patterns your senses need. With decoherence, the strange potential beneath reality becomes hidden behind a calm surface of records, positions, shapes, and histories. And perhaps this is the most beautiful part. The weirdness is not gone. It is still there in the laws, still visible when we isolate systems carefully, still powerful enough to build quantum technologies, still deep enough to challenge the way we think about reality. But daily life is too warm, too bright, too entangled with itself to let that weirdness remain exposed. The world around you is like a pond in heavy rain. Somewhere beneath the surface, tiny ripples might have formed perfect patterns, but raindrops are falling everywhere, spreading circles over circles until the delicate design disappears into ordinary motion. Decoherence is that rain. It does not prove the ripples were never there. It explains why you no longer see them. So when you look around and the world seems solid, clear, and definite, remember that this clarity is not the absence of quantum physics. It is quantum physics interacting with too much of everything at once. The room is not simple because nature is simple. The room is simple because the environment has already hidden the complexity. Decoherence is the universe's quiet way of covering its own strangeness, not by lying, but by spreading the truth so widely that only the stable outline remains. A particle's identity can become blurry. Imagine trying to place tiny name tags on the smallest pieces of matter, calling this one particle A and that one particle B, then watching quantum physics gently take the tags away and tell you that, in many situations, nature does not recognize the difference you are trying to draw. This is the strange idea that a particle's identity can become blurry. In ordinary life, identity feels obvious. One coin is not another coin. One grain of sand is not another grain of sand if you could follow it carefully enough. One person has a history, a position, a set of memories, a body that makes them distinct from everyone else. Even identical twins are not truly identical in this everyday sense. They occupy different places, experience different moments, and can be individually recognized. So when we imagine particles, we often picture tiny objects with private identities, like microscopic beads moving through space with invisible labels attached. But quantum physics changes that picture. Electrons, for example, are not merely similar to one another. As far as every experiment can tell, all electrons are exactly identical in their fundamental properties. Every electron has the same electric charge, the same mass, the same spin, the same way of responding to the forces it can feel. There is no scratch on one electron, no hidden serial number, no tiny difference that lets nature say, this is that particular electron from before. If two electrons are exchanged in a quantum system, the physical predictions do not change in the way they would for two labeled classical objects. This is not because our instruments are too weak to read the labels. The deeper point is that the labels do not appear to be part of reality at all. Identity, at this scale, is not like identity in the human world. It is not built from personal history in the ordinary sense. It is built from state, relation, and allowed behavior. If two identical particles are placed in a situation where their quantum states overlap, asking which particle is which can stop being a meaningful question. It is not that one particle is hiding behind the other. It is that the total quantum description may not allow a clean separation into this one and that one. The system contains particles, but their individuality can dissolve into the structure of the whole. This is especially important in atoms, where electrons do not behave like little planets each carrying a private orbit around the nucleus. The electrons in an atom are identical particles arranged according to quantum rules, and the atom's behavior depends on those rules of indistinguishability. One of the most important consequences is the Pauli exclusion principle, which applies to particles called fermions, including electrons. It says, in simple terms, that two identical fermions cannot occupy the exact same quantum state. This is not a small technical detail. It is one of the reasons atoms have structure. It helps explain why electrons fill atomic states in layers, why the periodic table has its shape, why chemical elements behave differently, and why matter has the richness we see in the world. Without this rule, electrons would collapse into the lowest available state. Chemistry would be radically different, and the stable complexity of ordinary matter would not exist in the same way. So the blurriness of particle identity is not an abstract puzzle with no consequences. It is written into the architecture of atoms, molecules, materials, and life. The fact that electrons cannot be individually tagged, combined with the rule that identical fermions avoid sharing the same state, helps build the layered order from which chemistry emerges. At the same time, there are particles called bosons, such as photons, that behave in almost the opposite way. Identical bosons can occupy the same state together, and when many do, remarkable collective behavior can appear. Laser light depends on photons acting in a coordinated way, sharing the same quantum state, so the light becomes highly organized. Bose-Einstein condensates, created in laboratories at extremely low temperatures, show atoms behaving collectively in a shared quantum state, almost as if many particles have softened into one larger quantum entity. In such cases, individuality becomes even more blurred. The particles have not vanished, but the system is no longer well understood as a crowd of tiny separate things, each doing its own private action. It becomes a collective state, a shared pattern, a kind of many-body unity that has no simple everyday counterpart. This is one of the places where quantum physics teaches a deep lesson about the difference between counting and identifying. You may know there are two electrons in a system, or many photons in a beam, but that does not mean each one carries a personal identity you can follow like a numbered marble. In certain quantum situations, the number can be meaningful while the individual labels are not. It is like hearing a choir note made from many voices so perfectly blended that you can say how many singers are present only through other evidence. But the sound itself no longer lets you point to one voice and separate it from the rest. Again, the analogy is imperfect because particles are not human singers, but it helps loosen the classical habit. Quantum identity is not always about separable individuals. It is often about patterns in a shared state. This becomes especially strange when particles are created and destroyed. In quantum field theory, particles can appear as excitations of fields and can be transformed in interactions. An electron detected today is not necessarily meaningful as the same individual electron in the way your childhood photograph and your present face belong to the same person. For stable particles, we can track effects and histories in practical contexts, but at the deepest theoretical level, identical particles do not carry personal biographies. If an electron enters a system of other electrons, asking which outgoing electron was the original one can be like asking which wave in the ocean is the same water shape after many waves overlap. The conservation laws may tell us that charge, energy, momentum, and other quantities are preserved, but the identity of a particular identical particle may not be something nature keeps as a separate fact. This is hard for the mind because we are storytellers. We want every object to have a continuous thread, a private line from past to future. Quantum physics often gives us a different kind of continuity, not the continuity of labeled individuals, but the continuity of properties, states, and lawful transformations. The particle's who may be blurry, while its what it can do remains sharply defined. And maybe that is the most important distinction. A particle's identity can become blurry without the physics becoming vague. Electrons are identical with astonishing precision. Their behavior follows strict rules. Systems of identical particles can be calculated, tested, and used in technology. The blurriness is not a failure of knowledge. It is part of the structure of the world. It tells us that individuality, which feels so fundamental in human experience, may not be fundamental in the same way for the smallest units of matter. At the quantum level, reality may care less about personal labels and more about relationships, symmetries, and allowed arrangements. The same kind of particle is not one member of a crowd with a secret face. It is an expression of a field with shared properties, entering into a state where separateness may or may not be meaningful. So when you think of a particle's identity becoming blurry, do not imagine confusion or disorder. Imagine nature refusing to waste reality on labels it does not need. Imagine many identical electrons building the shells of atoms, not because each has a private name, but because the whole arrangement obeys a deep rule of sameness and exclusion. Imagine photons joining into one clean laser beam, because their shared state matters more than their individuality. Imagine the smallest world not as a box of tiny named objects, but as a disciplined structure where identity can belong to the pattern rather than the piece. And as that thought settles, the visible world becomes more mysterious. Every object around you, every metal, every color, every chemical bond, every living cell, depends on particles whose individuality is not as simple as yours. Your world of named things rises from a deeper world where some things are so perfectly alike that nature itself stops treating them as separate characters and begins treating them as a shared possibility. That is the quiet wonder of quantum identity. Sometimes the universe does not ask which particle is which because at the deepest level, there may be no which to ask. Quantum interference can destroy an expected outcome. Imagine arranging an experiment so carefully that one detector should be waiting for a particle. One path should seem open, one outcome should appear possible, and yet when the quantum system is allowed to unfold, that expected result vanishes as if nature has silently crossed it out before it can happen. This is the strange force of quantum interference. It can destroy an outcome that ordinary thinking would expect to see. In everyday life, if there are two ways to reach the same result, you normally assume the result becomes more likely. 2 doors into a room should make it easier to enter. 2 roads to a city should increase the chance of arrival. 2 opportunities should strengthen the possibility. But in quantum physics, different possible ways for an event to happen do not always add like ordinary alternatives. They can combine more like waves with hidden timing. If the timing is aligned, the outcome can grow stronger. If the timing is opposed, the outcome can be weakened or removed. This is called destructive interference, and it is not just a pretty idea. It is measured, engineered, and used. A beautiful example comes from a device called a Machtsender interferometer. Imagine a single photon entering a carefully built arrangement of mirrors and beam splitters, where it has 2 possible routes before the paths are brought back together. If you think classically, you might expect the photon to have some chance of arriving at either of 2 detectors at the end. Both detectors seem physically available. Nothing obvious blocks one of them. But when the paths are balanced perfectly, quantum interference can make one detector click reliably while the other remains dark. That dark detector is not dark because the photon couldn't have gone there in a simple mechanical sense. It is dark because the possible contributions leading to that detector cancel. The outcome is physically available in the layout, yet the quantum rules erase it from the results. This is a profound lesson. In quantum physics, an outcome can be absent not because there is no path, but because the paths cancel each other. The emptiness itself is part of the evidence. You might look at the silent detector and think nothing happened there. But that silence is telling you something very specific about the invisible structure of the experiment. It says the alternatives remained coherent long enough to interfere. It says the possible routes were not behaving like separate ordinary stories. It says nature considered the full arrangement before producing a result. This is why interference is so different from simple randomness. If particles were merely arriving by blind chance, you would expect noise, scattered clicks, imperfect disorder. Instead, under the right conditions, you can get a perfectly suppressed outcome, a region of no detection, a missing result that appears again only when the delicate balance is disturbed. Change the path length slightly, rotate an optical element, introduce a material that delays one route, or allow information to leak about which path was taken, and the previously dark detector may begin to click. The expected outcome returns when the cancellation is broken. That sensitivity is what makes quantum interference both powerful and fragile. It depends on coherence, on keeping the alternatives related. If the system becomes too entangled with the surrounding environment, if heat or vibration or stray light records which route was taken, the alternatives stop combining cleanly. The cancellation fades and the world begins to look more ordinary again. But while coherence survives, interference can sculpt reality with astonishing precision. This is not limited to laboratory puzzles. Destructive interference is used in real optical technology. Anti-reflection coatings on lenses, for example, are designed so that reflected light waves from different surfaces cancel each other, reducing glare and letting more light pass through. That is a classical wave example, but it helps your intuition. Quantum interference takes this wave logic into the behavior of individual quantum systems, where even single photons, electrons, atoms, or molecules can show outcome suppression under carefully controlled conditions. In particle physics and chemistry, interference between different quantum pathways can increase or reduce the likelihood of reactions, emissions, or transitions. In quantum computing, the entire hope is not that a quantum computer simply tries every answer at once in a magical way, but that its operations can guide amplitudes, so wrong answers tend to cancel, while useful answers become more likely to survive measurement. That is a disciplined version of the same idea. Not every possible route deserves to become a result. Some must be strengthened, others must be erased. And this should make you think differently about absence. In normal life, absence often feels like lack. No sound, no light, no signal, no event. In quantum experiments, absence can be a signature of structure. A detector that does not click under the right conditions is not always boring. It may be showing that destructive interference is working. It may be revealing that 2 possible histories met in such a way that the final record was forbidden by cancellation, not by a wall. The missing outcome becomes as meaningful as the visible one. This is why quantum physics can feel almost like negative architecture. It builds not only with presences, but with carefully arranged absences. It shapes the world by deciding where something can appear and where it should disappear. Yet there is no fantasy here, no claim that reality can be cancelled by thought or desire. Quantum interference requires precise physical conditions. The system must be prepared properly. The alternatives must remain coherent. The apparatus must preserve the relationships that allow cancellation. The rules are strict, and the results are testable. When everything is arranged correctly, an expected outcome can be destroyed with a reliability that feels almost impossible to common sense. And when the arrangement is changed, the outcome comes back. That is the beauty. The disappearance is not random. It is controlled. It is lawful. It is nature's way of saying that possibility is not enough. For an event to happen, the possible ways toward it must survive their meeting with one another. So when you hear that quantum interference can destroy an expected outcome, imagine a stage with two spotlights aimed at the same place. But instead of making the stage brighter, they create darkness because their hidden rhythms oppose. Imagine a detector waiting patiently for a signal that never comes, not because the experiment failed, but because it succeeded too perfectly. Imagine a universe where the final result is shaped not only by what could happen, but by how the different ways of happening fit together. That is the quiet shock of quantum interference. Sometimes reality does not arrive because possibility cancels itself before it becomes fact, and the place where something should have been becomes the clearest evidence of the hidden order underneath. Symmetry shapes what particles are allowed to do. Imagine discovering that the universe is not governed only by forces pushing and pulling, but by deep hidden patterns that act like invisible rules of permission, deciding what particles may become, how they may transform, which interactions can happen, and which are forbidden before they even begin. This is the quiet power of symmetry in quantum physics. In everyday life, symmetry usually means visual balance, a butterfly's wings matching, a snowflake repeating its arms, a face appearing even on both sides, a circle looking the same after you turn it. But in physics, symmetry means something deeper. It means there is a transformation you can make without changing the essential truth of a system. Move an experiment from one side of a room to another, and the basic laws should still work. Turn the whole experiment around, and nature should not suddenly invent different rules. Perform the same process today or tomorrow, and the laws should remain consistent. These simple-sounding symmetries are not decorative. They shape the deepest structure of reality. They are connected to conservation laws, the great rules saying that certain quantities cannot simply appear or vanish. Because the laws of physics do not change from moment to moment, energy is conserved. Because empty space has no preferred position, momentum is conserved. Because space has no preferred direction, angular momentum is conserved. These are not random bookkeeping habits. They are the fingerprints of symmetry. And when you enter the quantum world, symmetry becomes even more powerful because particles are not just little things moving around. They are defined by the ways they respond to the symmetries of nature. An electron is an electron partly because it carries certain properties, such as electric charge and spin. And those properties tell us how it can interact. It cannot simply do anything. It cannot decay into just any collection of other particles. It cannot ignore charge conservation. It cannot break the rules of momentum, energy, or deeper quantum symmetries without leaving the theory behind. In this sense, symmetry is like the grammar of the particle world. A sentence may contain many words, but grammar decides which arrangements make sense. Particles may meet with enormous energy, but symmetry decides which outcomes are allowed. In particle accelerators, when protons collide at nearly the speed of light, the energy can produce showers of new particles. It may look chaotic from the outside, like nature exploding into fragments, but it is not free chaos. Every event must obey conservation rules. Charge must balance. Energy and momentum must balance. Certain quantum numbers must be respected, unless a specific interaction is known to violate them in a controlled way. The result is not anything can happen. The result is everything that happens must pass through the gate of symmetry. This is one reason physicists can predict particle behavior at all. Without symmetry, the microscopic world would be a lawless storm. With symmetry, even violent collisions become readable. The patterns of what appears and what never appears tell scientists which symmetries nature respects. Sometimes the absence of a process is as meaningful as the process itself. If a particle never decays in a certain way despite many opportunities, that silence may be pointing to a rule. If an interaction occurs rarely or only through one of the fundamental forces, that rarity may reveal which symmetry permits it and which one suppresses it. Symmetry also explains why particles fall into families. Quarks and leptons, the matter particles of the Standard Model, are not scattered randomly through theory. They fit into organized patterns of properties and interactions. The forces themselves are tied to symmetries called gauge symmetries. This phrase can sound intimidating, but the idea can be softened. Some symmetries are not just global patterns you see from far away. They are local rules that must hold at every point, and when nature respects those rules, force-carrying particles appear as part of the structure. The electromagnetic force, the weak force, and the strong force are deeply connected to this kind of symmetry. The photon, the particles that carry the weak interaction, and the gluons that bind quarks inside protons and neutrons are not added to the universe like extra decorations. They arise from the requirement that certain symmetries be preserved. That is astonishing. A force in this view is not merely a push. It is what happens when the universe insists on a certain kind of consistency. Symmetry becomes active. It becomes law. It becomes interaction. But nature is even stranger, because some symmetries are not perfectly visible in the world around us. They may be hidden or broken. Imagine a perfectly round table covered by a cloth. The table itself has symmetry, but if a ball rolls to one place and rests there, the situation now seems to choose a direction, even though the deeper structure did not. Physics uses a similar idea when discussing spontaneous symmetry breaking. A law may contain a symmetry, but the stable state of the system may not display it openly. This is central to understanding the Higgs field. Without going into heavy mathematics, the Higgs field fills space, and particles interacting with it can acquire mass. The symmetry structure of the electroweak theory is hidden in such a way that some force carriers become massive while the photon remains massless. This is not a simple visual symmetry like a mirror. It is a hidden symmetry in the equations of nature, and its breaking helps explain why particles behave as they do. The Higgs boson, discovered in 2012, was important because it confirmed a key part of this picture. The universe has a field whose presence shapes the masses of elementary particles. Again, symmetry did not merely describe beauty, it helped reveal why matter has the properties that allow atoms, chemistry, planets, and bodies to exist. There are also symmetries involving reflection and time that once seemed obvious, but turned out to be more subtle. You might think nature should behave the same in a mirror, but the weak interaction violates mirror symmetry, meaning some particle processes distinguish left from right in a fundamental way. That discovery shocked physics, because it showed that the universe is not always balanced in the ways human intuition expects. Later, scientists found that certain processes involving particles called kaons and b-mesons also violate a combination of charge and mirror symmetry. These violations matter because they may be connected to one of the biggest questions in cosmology: why the universe contains far more matter than antimatter. If matter and antimatter had been produced in exactly equal amounts and behaved with perfect symmetry, they might have annihilated into radiation, leaving no stars, no planets, no listeners, no you. Tiny departures from symmetry may be part of why anything made of matter exists at all. That is a breathtaking thought. Your body may depend not only on what nature preserves, but on the precise ways nature is not perfectly symmetric. Symmetry gives permission, but broken symmetry gives structure. Perfect sameness can be sterile. A small imbalance can let history unfold. This is why symmetry in physics is not just the study of balance. It is the study of balance, permission, restriction, and meaningful imperfection. It tells particles what roles they may play. It tells forces how they may operate. It tells transformations what they must conserve. It tells scientists where to look when something unexpected appears. If an experiment finds a process that violates a known symmetry, it is not a small detail. It may be a doorway to new physics. If a particle behaves in a way the standard model does not allow, it can suggest hidden forces, undiscovered particles, or deeper principles not yet understood. In this way, symmetry is both a map and a warning system. It shows where reality should be stable, and it highlights where mystery begins. And perhaps this is the most human part of the idea. The universe is not built only from stuff, but from rules about what stuff is allowed to do. The visible world rises from invisible permissions. A particle does not simply exist as an isolated speck. It belongs to a pattern of symmetries, and those symmetries decide its charges, its interactions, its stability, its possible transformations. Some particles live almost forever by particle standards because no allowed decay route is available under the rules. Others vanish quickly because symmetry permits them to transform. Some interactions are common because the gates are open. Others are rare because they must pass through narrower doors. So when you look at matter, do not imagine only tiny pieces filling space. Imagine a hidden legal system of nature, a deep grammar that tells every particle which sentences it can form. Symmetry shapes what particles are allowed to do, because reality is not merely a collection of objects. It is an order of possibilities constrained by patterns so deep that breaking or preserving them can decide whether atoms exist, whether forces work, whether stars burn, and whether the universe becomes empty light, or a world rich enough to ask why it is here. Quantum mechanics predicts without explaining why. Imagine finding a machine that can tell you, with astonishing accuracy, where a tiny flash will appear, how an atom will absorb light, how a material will conduct electricity, how a particle will scatter, and how long an unstable system is likely to survive. But when you ask the machine why reality works that way, it answers only with rules, patterns, and silence. This is one of the most uncomfortable truths about quantum mechanics. It predicts with breathtaking precision, yet it does not always explain why in the way the human mind longs to understand. In ordinary life, prediction and explanation feel connected. If you know why a glass falls, you can predict that it will hit the floor. If you know why seasons change, you can predict winter and summer. If you know why a car stops, you can predict what happens when the brakes are pressed. Explanation gives the mind a story, and the story makes the prediction feel satisfying. Quantum mechanics often refuses that kind of satisfaction. It gives you a formal structure that works. It tells you how to prepare a system, how that system changes when left alone, what results may appear when measured, and how likely each result is. It can calculate the colors atoms emit, the behavior of electrons in solids, the operation of semiconductors, the magnetic properties of particles, and the strange statistical patterns seen in experiments. It is not vague. It is not weak. It is one of the most successful scientific frameworks ever built. But its success has a strange emotional texture because it often says, "Here is what you will observe," without giving the deeper mechanical picture your intuition wants. Here is what is really happening underneath in familiar terms. That gap is not accidental. It lies at the heart of the subject. Classical physics usually allows you to imagine a hidden story. A planet follows an orbit because gravity bends its motion. A wave spreads through water because each part of the water pushes on the next. A thrown stone follows a path because its position and motion evolve continuously through time. Quantum mechanics gives you something more abstract. It gives you a state, rules for how that state evolves, and rules for what measurement results can be expected. But when a single event happens, when one detector clicks instead of another, when one possible outcome becomes the actual result, the theory gives probabilities, rather than a simple inner reason that feels like everyday cause and effect. It can tell you how often each outcome should appear over many trials, and it does that with remarkable accuracy. But for the individual event, the why this one, exactly now, question becomes difficult. Some physicists accept this as a basic feature of nature. Others believe there must be a deeper theory beneath quantum mechanics that we have not yet found. This is one reason interpretations exist. The Copenhagen-style view, many worlds, pilot wave theory, objective collapse models, relational interpretations, information-based approaches, each tries to tell a different story about what the mathematics means. They often agree on the predictions, but disagree on the picture behind them. That is what makes quantum mechanics so unusual. In many areas of science, disagreement about the story would lead to disagreement about the results. Here, different interpretations can guide your imagination in very different directions while leaving the laboratory predictions nearly the same. The experiment gives the numbers. The philosophy asks what the numbers are trying to say, and the answer is still debated. This does not make quantum mechanics unreliable. It makes it humbling. It shows that prediction and understanding are not always identical. You can know how to use a rule before you know why the universe has that rule. Human beings used fire long before they understood combustion. Sailors used the stars long before astrophysics explained them. Doctors used certain treatments before molecular biology clarified their mechanisms. In quantum physics, the situation is more extreme because the rules are not merely waiting to become a familiar mechanical picture. They may be telling us that familiar mechanical pictures are the wrong demand. Maybe the deepest level of nature is not built to satisfy the kind of why that works for falling stones and turning gears. Maybe asking for a tiny hidden movie behind every quantum event is like asking what color a musical note weighs. The question feels natural only because your mind is using the wrong category. And yet, the hunger for why is not foolish. It is the engine of science. Without that hunger, no one would have looked beyond old models. No one would have tested strange predictions. No one would have built better theories. The danger is not asking why. The danger is demanding that the answer must resemble the world your senses already know. Quantum mechanics may be teaching us a new kind of explanation, one based less on pictures and more on structure. It explains by showing what can be consistently predicted, what cannot be jointly known, which transformations preserve information, which quantities are conserved, which outcomes are allowed, and how repeated experiments build stable patterns from individual uncertainty. This is explanation, but it is not always storytelling. It is not always a little object doing a little action for a little reason. Sometimes it is a map of constraints. Sometimes it is a grammar of possibility. Sometimes it is a rule book so accurate that the absence of a familiar picture becomes part of the lesson. Think of atomic spectra. Quantum mechanics can explain why atoms emit and absorb only certain colors by describing their allowed energy states and transitions. That is a genuine explanation. But if you push further and ask why nature uses quantum states at all, why probability enters in this particular way, why measurement gives one result, why the rules have exactly this form, the ground becomes less certain. At some point, every science reaches bedrock where it says, this is how nature behaves, as far as we can tell. Quantum mechanics reaches that bedrock in a place that feels especially strange because the behavior does not match common sense. It gives us control without total comfort. It gives us technology without final metaphysical peace. It lets us build lasers, transistors, atomic clocks, quantum sensors, and medical imaging tools, while still leaving philosophers and physicists arguing about what reality is doing when no result has yet been recorded. That contrast is almost poetic. The theory that powers the modern world also keeps the deepest question open. And maybe that is why quantum mechanics feels so alive after more than a century. A finished theory would feel like a locked room. Quantum mechanics feels like a room full of working instruments and unanswered echoes. You can trust the instruments. You can use them. You can build with them. But the echo remains. Why these rules? Why this kind of probability? Why this transition from possibility to fact? Why a universe that can be calculated so well and pictured so poorly? The honest answer is that we do not fully know. Not in the final satisfying sense. But ignorance here is not emptiness. It is a frontier marked by extraordinary success. Quantum mechanics predicts without explaining why. because it may be showing us that reality is deeper than the human need for a familiar cause story. It gives us the shape of what happens before it gives us the comfort of meaning. And perhaps the mature response is not to reject the theory because it feels incomplete, or to pretend it answers everything because it works so well, but to hold both truths gently. Quantum mechanics is one of the most accurate tools ever created, and it still leaves the universe mysterious. It teaches us that knowledge can be powerful before it is complete, that precision can coexist with wonder, and that sometimes science does not end the question. Sometimes science makes the question sharper, quieter, and more worthy of being asked. Reality becomes definite only in certain conditions. What if reality is not always born as a finished statement, but becomes definite only when the right physical conditions allow the world to keep a record of what has happened? This is one of the most careful and important ways to understand quantum physics without turning it into fantasy. At the scale of daily life, definiteness feels automatic. A glass is on the table, a door is closed, a shadow falls across the floor, a footprint remains in sand. The world seems to arrive already decided, already written into objects before you notice them. But quantum physics shows that, at smaller scales, definiteness is not always the starting point. It can be an outcome. A tiny system may be described by several possible results before an interaction, but those possibilities do not all become part of the public world in the same way. For reality to become definite in practice, certain conditions must be met. The system must interact strongly enough with something else. The possible outcomes must become distinguishable, and the result must be amplified or recorded so that it can persist. A detector click is definite because it is not just a private whisper inside the quantum system. It becomes a physical mark. An electrical pulse travels through a circuit. A screen changes at one point. A chemical grain darkens. A memory device stores a value. The result has left the small, delicate space of possibility and entered the larger world of records. This is why measurement in quantum physics is not simply someone noticing. A human mind is not required to make an electron real. What matters is whether the physical world has created a stable trace that separates one outcome from the others. A single photon hitting a photographic plate can trigger a chemical change. A particle passing through a detector can create a cascade of signals. A microscopic event can be magnified into something macroscopic, something robust enough that many observers could later agree on it. That amplification is one of the conditions that makes definiteness possible. Before amplification, the quantum description can remain delicate, reversible in principle, and sensitive to hidden relationships between alternatives. After amplification, the result becomes part of the world's history. It is no longer a fragile possibility that can easily recombine with other possibilities. It has become a fact with consequences. But this does not mean every interaction immediately creates the kind of definite reality you experience. Conditions matter. If a quantum system is isolated well enough, its alternatives may remain coherent, able to influence one another. If the interaction is too weak, or if no information about the alternatives becomes available, the system may not settle into a clear classical record. This is why physicists can perform weak measurements, delayed choice arrangements, and interference experiments, where the boundary between possibility and fact must be handled with great care. Nature does not simply flip from unreal to real in a dramatic theatrical moment. The transition toward definiteness depends on how much information has been copied into the environment, how clearly the alternatives can be distinguished, and whether the record becomes effectively irreversible. That word, irreversible, is important. In the deepest equations, some processes can look reversible, meaning that if you had perfect control over everything, you might imagine unwinding them. But the real world contains too many particles, too much noise, too many uncontrolled degrees of freedom. Once information spreads into the environment, it becomes practically impossible to gather it back. A result becomes definite, not because the universe stamps it with a mystical label, but because the information has dispersed so widely that, for all practical purposes, the alternatives can no longer interfere. This is why the world feels solid and settled. Not because the quantum layer is gone, but because the conditions around large objects constantly favor stable records. Light bounces off them, air touches them, heat radiates from them. Their states are copied again and again into the environment. Some physicists call this kind of spreading of information quantum Darwinism, a name that means only that certain states become selected because they are copied redundantly into the environment. A chair's position becomes definite to us because many fragments of the environment carry the same information about it. Photons scatter from the chair into your eyes, into the walls, into the room. Many observers can look from different places and agree that the chair is there because the information is not hidden in one private place. It is broadcast. Definiteness, then, is tied to shareability. A fact becomes classical when it can be independently accessed, copied, and compared without being destroyed by the first glance. A fragile quantum state cannot be copied in that simple way, but a classical record can. This is one of the deep differences between the quantum and classical worlds. The quantum world preserves delicate relationships. The classical world preserves stable records. Reality becomes definite only when the physical situation allows a potential outcome to become a record that survives. This is also why the apparatus matters. A measuring device is not just a passive observer. It is built to turn a microscopic event into a macroscopic signal. It is designed to make alternatives separate, to magnify one result, to prevent the result from remaining hidden in a fragile state. If the detector is poorly designed, too noisy, too weakly coupled, or unable to distinguish the alternatives, then the event may not become clear. The question nature answers depends on the conditions under which the question is physically asked. Ask in a way that preserves coherence, and you may see interference. Ask in a way that extracts which result information, and the system becomes definite in that basis. This is not subjectivity, it is physical context. A thermometer must touch or interact with what it measures. A camera must collect light. A particle detector must exchange energy with the particle. Every fact has a doorway through which it enters the recordable world. In quantum physics, that doorway is not optional. It defines what kind of fact can appear. And this should change how you think about certainty. Certainty is not always waiting underneath experience like a stone under cloth. Sometimes certainty is manufactured by the conditions of interaction, record making, and environmental stability. The world you know is filled with definiteness because it is filled with conditions that produce definiteness. But in quiet, isolated, carefully protected systems, nature can hold back from that settled form. It can remain in a state where multiple outcomes are still part of the active description, not because reality is weak, but because no condition has yet forced one outcome to become a durable public trace. So when you look at a definite object, remember that definiteness itself has a history. The object's position, shape, and state are not just abstract facts floating outside the world. They are maintained by continual interaction, by countless physical records, by information spreading through the environment faster than your awareness can follow. Reality becomes definite only in certain conditions because facts are not merely things that exist. They are things the universe has stabilized enough to remember. Beneath the calm surface of daily life is a deeper rule. The possible becomes actual when the world creates a record strong enough to last.